Look at the path the planets trace across the night sky. That thin band, 8 worlds, 4.5 billion years of motion, almost no vertical scatter, is not a feature of this solar system. It is the universe's own geometry, written in orbits. 98% of this system's rotational motion belongs to 4 worlds you have never visited. Earth contributes less than 1%. Between a collapsing gas cloud and the band of planets visible tonight, there is one unbroken causal chain. Tonight, you are going to follow that chain to its deepest root, a theorem proven in 1915, and why the answer has nothing to do with the solar system at all. There is a question hiding inside this familiar observation, and it is more difficult than it looks. Most people who think about the flatness of the solar system for the first time arrive at a quick answer. The planets all formed from the same spinning disk of gas and dust. The disk was flat, so naturally the planets that grew inside that disk ended up in the same plane. Simple, clean, satisfying. But that answer, though it contains truth, is not the whole truth. It is a placeholder that gestures toward the real explanation without actually reaching it. Because the moment you ask the next question, why was the disk flat in the first place, the answer stops being obvious. And the moment you ask the question after that, why does a collapsing cloud of gas become a disk at all, rather than a sphere or a chaotic swarm, you begin to realize that the flatness of the solar system is not a given. It is an achievement. Something that had to be created by physics, maintained by physics, and defended against the constant tendency of chaotic systems to scatter in all directions. Everyone knows that the planets go around the sun. The textbook answer is that they orbit in roughly the same plane. You probably think this is simply because they all came from one flat spinning thing, and that flat spinning thing came from some original rotation in the collapsing cloud. That picture is almost entirely insufficient, because it skips over the single most important and counterintuitive step in the whole story. The reason that a vast, three-dimensional, turbulent, and chaotic cloud of gas can ever become something as precise and orderly as a disk at all. The solar system is flat for the same reason a spinning ballerina pulls in her arms and spins faster. But that analogy, satisfying as it sounds, only begins the explanation. Angular momentum, the momentum involved in spinning and circling, is conserved in the absence of a net torque, meaning the total rotational motion of a system remains constant. That is the law underneath everything. And it turns out to be a law with extraordinarily powerful consequences for the shape of things in the largest and most violent environments the universe creates. To understand why all the planets orbit in the same plane, we have to start much earlier than the planets. We have to go back to before the sun existed, before the solar system existed, back to a cold, dark, invisible place called a molecular cloud, somewhere in the spiral arm of the Milky Way galaxy, somewhere between 4 and 5 billion years ago. Picture yourself in that early darkness. Not the darkness of a cloudy night or a windowless room, but something deeper and more complete. A region of space where the density is higher than the void around it, though still almost unimaginably thin by any standard you would recognize. These vast clouds of gas and dust are called giant molecular clouds, and spiral galaxies like the Milky Way are estimated to contain roughly 1,000 of them, most located in the spiral arms. They are among the largest objects in galaxies, with physical dimensions spanning 10 light-years to as much as 1,000 light-years. Inside these clouds, the dominant ingredient is molecular hydrogen. Hydrogen atoms locked into pairs, drifting in temperatures not far above absolute zero. There is dust as well, microscopic grains of silicate and carbon and ice, the processed remains of long-dead stars from previous generations. The space between the stars is strewn with microscopic dust grains, an accumulation of the ejected matter of many long-dead stars. These dust particles probably formed in the cool atmospheres of old stars, then grew by accumulating more atoms and molecules from the interstellar gas within the Milky Way galaxy. The cold, the density, the dust, all of it is essential. These are the raw materials from which solar systems are eventually made, including this one. But a molecular cloud left entirely alone will not simply collapse into a star. Something has to push it over the edge. A nearby supernova, perhaps, sends a pressure wave rolling through space. A ripple of density that compresses part of the cloud past a critical threshold. Or two spiral arms of the galaxy pass close enough to create gravitational stirring. Whatever the trigger, some region of the cloud begins to contract under its own weight, and once that process begins, it tends to continue. Gravity is not easily stopped once it has gained the upper hand. Here is the first hidden complexity in the story of flatness, and it arrives before a single planet has formed. That original molecular cloud was not sitting still. Nothing in the universe sits perfectly still. Every cloud, every accumulation of matter at any scale, carries some residual rotation, some small, almost imperceptible spin imparted by the motion of surrounding matter, by asymmetries in the cloud's own structure, by the gentle gravitational tugging of neighboring clouds and stars. It is unlikely that such a nebula or any astrophysical gas collapses with zero angular momentum, and so the gas is probably initially spinning at least slowly. Because of the conservation of angular momentum, the cloud spins faster as it contracts. This is the key. This is where the architecture of the solar system begins to be decided. Not in some violent or dramatic moment, but in the quiet, almost invisible rotation of a vast, cold cloud. A rotation so slow that a full turn might take millions of years. A rotation that seems, from any reasonable perspective, to be negligible. And yet it is not negligible. Because of one of the most powerful and unforgiving laws in all of physics, that tiny spin will be amplified into something that shapes a solar system. Think about what happens to a figure skater who pulls their arms toward their body while spinning. Their rotation rate increases dramatically, not because they push off the ice harder, but because the same amount of angular momentum, that product of mass, velocity, and radius, has to be conserved in a smaller space. The arms come in, the radius shrinks, and the spin accelerates to compensate. This is conservation of angular momentum in action. It is not a metaphor for what happens to a collapsing cloud. It is the same physics, operating at a scale trillions of times larger, over timescales millions of times longer. The initial collapse of a solar mass protostellar nebula takes around 100,000 years. Every nebula begins with a certain amount of angular momentum. Gas in the central part of the nebula, with relatively low angular momentum, undergoes fast compression and forms a hot hydrostatic core containing a small fraction of the mass of the original nebula. This core forms the seed of what will become a star. As the collapse continues, conservation of angular momentum means that the rotation of the infalling envelope accelerates, which largely prevents the gas from directly accreting onto the central core. The gas is instead forced to spread outward near its equatorial plane, forming a disk, which in turn accretes onto the core. Listen to those last few sentences carefully, because this is where flatness comes from. Not from the original rotation being perfectly aligned with some cosmic axis. Not from some pre-existing flat structure, but from physics. from the fact that material falling inward in the polar directions, near the top and bottom of the collapsing sphere, faces less resistance from centrifugal effects, so it falls straight in toward the growing protostar. But material in the equatorial zone, spinning faster and faster as the radius shrinks, cannot fall all the way in. The rotational motion pushes outward with a force that balances gravity, and so that material stalls. It spreads sideways. It forms a sheet. Because of the competing forces associated with gravity, gas pressure, and rotation, the contracting nebula begins to flatten into a spinning, flattened shape with a bulge at the center. The reduced angular momentum support near the poles means that it is easier for material to fall in near the top rather than at the equator, and there is therefore a bulge, which eventually leads to a disk. There is something profound happening here that deserves more than a sentence. The universe is sorting material by its relationship to rotation. Particles that happen to be moving in the plane of the cloud's net rotation end up being supported against infall. Particles that are not moving in that plane, or that are moving in conflicting directions, collide with other particles. Those collisions dissipate energy. The random component of motion, the chaotic up and down, back and forth jitter of individual gas molecules, bleeds away as heat. But the net rotational component cannot bleed away. There is nowhere for angular momentum to go. So what remains after all the collisions, after all the energy dissipation, is pure rotation. Orderly, flat, persistent. As the nebula collapses, clumps of gas collide and merge. Their random velocities average out into the nebula's direction of rotation, producing orderly motion. The spinning nebula then assumes the shape of a disk. This is not a metaphor, this is the actual physical mechanism. Chaos averaging out into order, random motion converting into coherent rotation. The disk does not emerge because the cloud was shaped like a disk to begin with. The disk emerges because physics has one direction, the net angular momentum direction, that it cannot erase, and everything else gets sorted and collapsed and simplified until only that one direction remains. Formation of protoplanetary disks from the collapse of prestellar and protostellar cores in molecular clouds is a natural consequence of angular momentum conservation. The subsequent evolution of such a disk into the present-day solar system, in which more than 99% of the mass is within the Sun, and more than 99% of the angular momentum is carried by the planets, required the inward transfer of mass. Stay with this for a moment, because this is one of the most remarkable facts in all of planetary science. The Sun contains more than 99% of the mass of the solar system, and yet the planets carry more than 99% of the angular momentum. The Sun rotates slowly, far more slowly than the conservation of angular momentum from the original cloud would predict. How? Something transferred that angular momentum outward from the forming Sun to the surrounding disk, and, eventually, to the planets themselves. One possible explanation suggested by Hannes Alfvén was that angular momentum was shed by the solar wind during the star's T Tauri phase. The momentum is transported to the outer parts of the disk by viscous stresses. Viscosity is generated by macroscopic turbulence, but the precise mechanism that produces this turbulence is not well understood. Another possible process for shedding angular momentum is magnetic braking, where the spin of the star is transferred into the surrounding disk via the star's magnetic field. This is the first of the genuine uncertainties in this story, and it deserves to be named as such. We understand why a disk forms. We understand why the planets that grew in that disk ended up in the same plane. But the detailed physics of how angular momentum was redistributed within the early solar system, exactly how the Sun lost its spin to the disk, exactly which mechanisms dominated, exactly how turbulence was generated and maintained in the protoplanetary disk. These are areas where science is still actively working. Some researchers favor magnetic braking as the dominant mechanism. Others emphasize the magnetorotational instability, a process by which weak magnetic fields in a differentially rotating disk amplify into turbulence that transports angular momentum outward. The honest answer is that we do not yet have a complete, settled picture of the angular momentum problem. Here is what makes this story strange. The first person to guess the answer correctly was a philosopher in 18th century Prussia, working in 1755, with no telescope worth speaking of, no equations for angular momentum conservation, and no concept of a nebula in the modern sense. He guessed it from pure logic. And then, for nearly 2 centuries, science decided he was wrong. His name was Immanuel Kant. If you love exploring the architecture of the cosmos as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. I read every comment. In a work titled Universal Natural History and Theory of the Heavens, published anonymously when he was 31 years old, Kant proposed that the sun and planets had condensed out of a vast, rotating cloud of gas. The rotation, he argued, would naturally cause the cloud to flatten as it collapsed. Planets would form within the resulting disk. The shape of the solar system would inherit the geometry of the disk that produced it. He could not prove this. He had no equations to back it up. He was a philosopher reasoning from first principles in a small city on the Baltic Sea, and the closest thing he had to evidence was the naked eye observation that the planets all moved in nearly the same plane. But he saw the shape of the answer. He saw it more than 2 centuries before any human being would directly imagine a protoplanetary disk around another star. 41 years later, in 1796, the French mathematician Pierre-Simon Laplace published the same idea in more developed form, in his Exposition du système du monde. Laplace was one of the great figures of mathematical physics, and his version of the nebula hypothesis carried weight Kant's had never had. The sun and planets, Laplace argued, began as a whirling cloud of gas. The cloud collapsed into a star. The remaining material spun outward into a flat disk, which then formed planets. For most of the 19th century, the Kant-Laplace nebula hypothesis was the standard model of solar system formation. And then it broke. The problem was angular momentum. The planets, it turned out, carry 99% of the solar system's rotational motion, while the sun carries less than 1%, even though the sun contains more than 99% of the mass. This is the inverse of what a simple Laplacian collapse should produce. James Clerk Maxwell and James Jeans pointed out that the material spun out by Laplace's mechanism would not have enough gravity to pull itself back together into planets. The math did not work. The hypothesis was dismissed. For the first half of the 20th century, scientists turned to other models: passing star encounters, tidal disruptions, catastrophic events of various kinds. None of them worked better. The nebula hypothesis sat on the shelf, considered an interesting but failed idea from an earlier century. It was rescued by a Soviet astronomer working in Moscow. The birth of the modern, widely accepted hypothesis of planetary formation, the solar nebula disk model, can be traced to the works of Viktor Safronov. Safronov's 1969 monograph, translated into English in 1972, laid out how planets could grow from small particles in a protoplanetary disk through a process of accumulation and collision. His work transformed the field, providing the theoretical scaffolding that subsequent generations of researchers would build upon. Today, The solar nebula disk model is the dominant framework for understanding not just our solar system, but planetary systems throughout the galaxy. The flatness of the solar system, then, is not a coincidence. It is not an accident of how things happen to fall together. It is the direct, inevitable consequence of one physical law: conservation of angular momentum, operating on the most chaotic and large-scale systems the universe produces. That law takes a turbulent, three-dimensional, irregularly shaped cloud of cold gas and sculpts it, over the course of 100,000 years, into a precise, thin, rotating sheet. And everything that forms inside that sheet, every world, every moon, every ring system, every drifting asteroid, inherits the geometry of the disk. That is the foundation of the answer. But it is only the foundation. The deeper you look, the more intricate the story becomes. The invariable plane of a planetary system, also called Laplace's invariable plane, is the plane passing through its barycenter, its center of mass, perpendicular to its angular momentum vector. In our solar system, about 98% of this effect is contributed by the orbital angular momenta of the four giant planets: Jupiter, Saturn, Uranus, and Neptune. The invariable plane is within half a degree of the orbital plane of Jupiter, and may be regarded as the weighted average of all planetary orbital and rotational planes. Here is a number that should bother you. The Earth, your home, the planet from which every astronomical observation in human history has been made, the reference point for every star chart ever drawn, contributes less than 1% of the solar system's angular momentum. Less than 1%. Mercury, Venus, Earth, Mars, the four worlds we live among, the four worlds that humans have walked on or sent spacecraft to the surface of, together carry barely 2% of the rotational motion that defines the geometry of this system. We are, from the perspective of the physics that holds the solar system flat, essentially passengers. The remaining 98% belongs to four worlds that no human has ever set foot on, and almost certainly never will. Jupiter alone carries 60.3% of the solar system's total angular momentum. Saturn carries 24.5%, Neptune 7.9%, Uranus 5.3%. Four giant planets account for 98% of everything. The plane you call the ecliptic, the plane of Earth's orbit, the reference frame of nearly every astronomy lesson you have ever heard, is not the true geometric center of the solar system. It is just our local viewpoint. The actual mid-plane of this system, the plane around which everything is genuinely organized, belongs to Jupiter. This fact will become important later when we look at why the planets in our solar system are as flat in their orbits as they are, and why other planetary systems orbiting other stars are sometimes far less orderly. Because the presence of giant planets turns out to be both a creator and a regulator of orbital flatness. And in some systems, giant planets are not regulators. They are disruptors. The flatness you observe in the night sky when you trace that thin arc of planets from horizon to horizon is the fossilized geometry of a disk that no longer exists. The gas and dust of the protoplanetary disk dispersed long ago, blown away by the young sun's radiation and solar wind, cleared out by the forming planets themselves. The typical lifespan of accretion disks is a few million years, with most observations indicating around 3 to 10 million years. By the time a star reaches the classical T Tauri stage, the disk becomes thinner and cools. What remains, 4.5 billion years after that disk dissolved, is the orbital memory of its geometry. The planets move in the plane where the disk once was. They will continue to move in that plane essentially forever, because there is nothing with sufficient gravitational leverage to pull them out of it. This is the opening of the real story. The flatness of the solar system is a message from the past, written in the orbits of worlds, describing the physics of a disk that burned out before the Earth was finished forming. In the sections ahead, we will read that message carefully, following each step in the causal chain, from cold cloud to spinning disk, from spinning disk to planet building, from planet building to the orderly arrangement of worlds you can see on any clear night. And we will find along the way that the story is not as clean as the textbooks suggest. There are complications. There are exceptions. There are other solar systems found in the past few decades where the planets do not behave so obediently, where giant worlds orbit their stars at wild angles, where whole planetary systems tilt away from the equatorial plane of their own star, where the rules that govern our neat, flat solar system appear to have been broken or never applied in the first place. Those exceptions are not embarrassments to the theory. They are illuminations of it. They show us, by contrast, exactly how special and how fragile the flatness of a planetary system actually is. They show us what can go wrong, what forces can scramble the orderly inheritance of the disk. And they show us that our own solar system, with its nearly perfect coplanarity, is in some ways a fortunate accident, a configuration that required not just the right physics, but also the right initial conditions, and perhaps also a degree of dynamical calm that not every planetary system enjoys. The planets orbit in the same plane. That is where we began. And by the time we reach the end of this journey, you will understand that simple sentence at a depth that transforms it into something far more remarkable than it first appeared. The disk is gone. That much is worth sitting with for a moment. The physical structure that gave the solar system its shape, the swirling sheet of gas and dust that stretched from the young sun out past where Neptune now orbits, dissolved roughly 4.5 billion years ago. It was consumed, partially absorbed into the growing planets, partially blown away by the force of the young sun's light and wind, partially dissipated by the heat of its own internal processes. What remains is only the gravitational memory of its geometry. The planets loop through space in the plane where the disk once was, not because anything is holding them there now, but because there is nothing with enough force to move them elsewhere. This is the first layer of the real story. The flatness you can observe tonight is a fossil. And like all fossils, it tells you something about a living thing that no longer exists. Now we need to understand that disk in more detail. Not just that it existed, but how it worked. What went on inside it? What forces shaped it, maintained it, and ultimately destroyed it? Because the disk is not a passive backdrop in the story of the solar system's flatness. It is the protagonist. Everything that happened after its formation happened within it, constrained by it, shaped by it. Picture the disk as it would have appeared roughly 4.5 billion years ago, while the solar system was still in its formative stages. The young sun is at the center, blazing with the energy of gravitational contraction before nuclear fusion has fully stabilized. It is surrounded by a vast, spinning sheet of gas and dust extending outward for hundreds of astronomical units. An astronomical unit being the average distance from the Earth to the Sun, roughly 150 million kilometers. But this disk is not uniform. It is stratified by temperature. Close to the Sun, where temperatures are highest, only the most refractory materials, iron, nickel, minerals with extremely high melting points, can exist in solid form. Everything else is vapor. The high temperature in the inner disk causes most of the volatile material, water, organics, and some rocks, to evaporate, leaving only the most refractory elements like iron. The ice can survive only in the outer part of the disk. This creates a crucial dividing line in the disk, a boundary beyond which ice and other volatile compounds can survive in solid form. This boundary is called the ice line, or sometimes the frost line or snow line, and it sits at roughly 2 to 3 astronomical units from the young sun, somewhere in what is now the outer part of the asteroid belt. That boundary matters enormously for the architecture of the solar system, and it matters for the flatness story in a subtle but important way. Inside the ice line, the solid material available for planet building is limited to metals and silicates. These are the building blocks of the terrestrial planets: Mercury, Venus, Earth, and Mars. They are small worlds, dense, made of rock and metal, because there simply was not enough solid material close to the Sun to build anything larger. Outside the ice line, the situation changes dramatically. Ice, frozen water, methane, ammonia, and other volatile compounds, is available in solid form, enormously increasing the total mass of solid material. Planetary cores that form beyond the ice line can grow much larger, and once they exceed a critical mass of roughly 10 Earth masses, they can begin to gravitationally capture the hydrogen and helium gas that permeates the outer disk, growing into gas giants: Jupiter, Saturn, Uranus, and Neptune. Why does this matter for flatness? Because those gas giants grew so large that they dominated the angular momentum budget of the solar system. And because they grew within the disk, their orbits are most precisely aligned with the disk's midplane, the invariable plane of the solar system, the plane passing through its center of mass, perpendicular to its total angular momentum vector, is within half a degree of the orbital plane of Jupiter, with about 98% of this effect contributed by the orbital angular momenta of the 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. The geometry of the solar system, in other words, is Jupiter's geometry. Everything else is a rounding error. This is the first place in the story where the textbook answer's apparent simplicity breaks down. You probably think of the flatness of the solar system as a uniform property, shared equally by all 8 planets. The textbook picture is a flat disk with 8 worlds neatly embedded in it, all equally contributing to its planarity. That picture is almost entirely wrong, in the sense that it misses the most important quantitative fact. The solar system's flatness is not a democracy of worlds. It is a consequence of 4 massive planets dominating the angular momentum budget so completely that the other 4 planets, along with all the moons, all the asteroids, and all the comets, are essentially irrelevant to the shape of the system. Jupiter alone contributes 60.3% of the solar system's total angular momentum. Saturn contributes 24.5%. Neptune contributes 7.9%. Uranus contributes 5.3%. Add those up, and you have 98% accounted for by 4 worlds. The rest, Mercury, Venus, Earth, Mars, Pluto, every asteroid, every comet, contributes the remaining 2% between them. The Earth, our home, our reference point for all of astronomy, contributes less than 1% of the angular momentum that defines the plane of the solar system. There is something quietly humbling about that number. We measure the solar system's orbital geometry in terms of the ecliptic, the plane of Earth's orbit around the Sun, because that is our vantage point. But the ecliptic is not actually the most fundamental plane in the solar system. In general, the ecliptic is taken as the reference plane in studies of solar system dynamics, although there is no dynamical reason for doing so. The invariable plane, as originally defined by Laplace, seems to be a far more natural choice. It is Jupiter's orbital plane, not Earth's, that most nearly represents the true midplane of the solar system. Earth just happens to orbit close enough to that plane, the two differ by only about 1.5 degrees, that the distinction rarely matters for casual skywatching. But dynamically, philosophically, there is a difference. The center of gravity of this system, in every meaningful sense, belongs to the giants. Back in the disk, formation is underway. The mechanisms by which small grains of dust grow into full-sized planets represent one of the most active and genuinely uncertain areas of planetary science. And understanding them is essential for understanding why the planets ended up as flat in their orbits as they did. The process begins at the smallest possible scale. The space between the stars is strewn with microscopic dust grains, an accumulation of the ejected matter of many long-dead stars. These dust particles probably formed in the cool atmospheres of old stars, then grew by accumulating more atoms and molecules from the interstellar gas within the Milky Way galaxy. These grains enter the protoplanetary disk as part of the original collapsing cloud. In the disk, they settle. Gravity pulls them gently toward the disk's midplane, the thinnest, densest part of the disk, where the concentration of material is highest. Dust grains drift downward, accumulating in a thin sublayer at the midplane, growing through gentle collisions as they do. Observations confirm directly that large millimeter-sized grains are subject to significant vertical settling in protoplanetary disks. The disk is not just flat in its overall geometry. Its building materials are themselves settling toward the flattest possible layer within it. The geometry is self-reinforcing at every scale. This settling is a delicate process, and here is where the first real complication enters. The dust grains settle toward the midplane, but the gas does not. Gas in a protoplanetary disk is supported against gravity partly by pressure, which means it can remain extended vertically even as the dust layer thins. This creates a situation where the dust layer is spinning at a slightly different velocity than the surrounding gas. The dust moves at near Keplerian orbital speed, while the gas, pressure-supported, moves slightly slower. This velocity difference creates a headwind for the dust particles, and that headwind causes them to lose angular momentum and drift inward toward the Sun. The inward drift of dust is one of the central challenges in planet formation. Particles need to grow fast enough to avoid being lost to the Sun before they reach planetesimal size. Stop here, because what comes next is something planetary science textbooks do not advertise. We do not actually know how planets form. We know the beginning, tiny grains of dust drifting in the disk, sticking gently when they collide. And we know the end. Finished worlds. Earth, Mars, Venus, Jupiter, orbiting in the plane. But the middle, the bridge between a speck of dust and an object large enough for gravity to take over, is an open problem in physics. The Earth exists. You exist. The rock under your feet was assembled by a process that researchers describe as the single biggest unsolved problem in the nebular disk model. This is not a casual admission. It is the core difficulty at the heart of planet formation theory. We understand, broadly, how tiny dust grains grow through gentle sticking collisions. And we understand, broadly, how kilometer-sized planetesimals grow through gravitational attraction. But the intermediate range, the regime where particles are perhaps a centimeter to a kilometer in size, too large for sticking forces to dominate, astronomers, but too small for gravity to take over, have been able to count and characterize stars. The classic and entire spiral remains the main framework for planet building today, a middle whereby very small particles are required to grow through collisions, Andromeda large with a destination, boulders, us, and eventually planetesimals. However, given the short lifetimes of disks, typical 5 million years, some models requiring an increase in the dust concentration in the midplane have been proposed to speed up grain growth up to planetesimal scales. For instance, based on streaming instability and pebble accretion. The streaming instability is a fascinating piece of physics that deserves attention, both because it is genuinely beautiful and because it is directly relevant to the flatness story. In the disk's midplane, where dust particles are concentrated, something counterintuitive can happen. Rather than the headwind from the gas uniformly draining the particles' angular momentum and sending them spiraling inward, groups of particles can collectively change the gas flow around them. Clumps of particles partially shelter each other from the headwind, reducing the inward drift. More particles accumulate in those clumps, further reducing the drift, attracting still more particles. The process runs away, concentrating dust into dense filaments, and then, very rapidly on astronomical timescales, collapsing those filaments gravitationally into planetesimals, kilometer-sized bodies that have enough self-gravity to resist disruption. This mechanism is beautiful, partly because it happens in the disk midplane. The streaming instability is most effective where the dust-to-gas ratio is highest, which is precisely in the thin central sublayer of the disk. It creates planetesimals that are born flat, born in the plane, born with orbital inclinations very close to zero. The flatness is baked in from the very moment the building blocks of planets first assemble themselves. From planetesimals, growth continues through a process called accretion, the capture of smaller bodies by larger ones through gravitational attraction and physical collision. The largest planetesimals in any region grow fastest because their greater gravity allows them to sweep up material from a wider region. Smaller planetesimals are captured, absorbed, broken apart, and reassembled. Over millions of years, a few dominant bodies, called planetary embryos, emerge from each annular zone of the disk. These embryos are moon-sized to Mars-sized objects, still confined to near-circular, near-coplanar orbits, because they grew in the disk, and the disk imposes discipline on their motions. The disk plays an active role in maintaining this discipline. A process called Type 1 migration causes planetary embryos to exchange angular momentum with the surrounding gas disk, producing a torque that modifies their orbital parameters. Crucially, the disk tends to damp orbital inclinations, to push objects back toward the midplane when they stray. It is a restoring force built into the physical environment of planet formation. As long as the disk exists, it acts as a conserving mechanism, keeping the growing planets in the plane. But the disk is also temporary. The lifespan of accretion disks is about 10 million years. By the time the star reaches the classical T Tauri stage, the disk becomes thinner and cools. Multiple mechanisms contribute to the disk's eventual dispersal. The young sun's radiation pressure pushes gas outward. The solar wind carries away material. The growing planets themselves clear gaps in the disk through their gravitational influence. And eventually, the disk simply runs out of material to sustain itself. Once the disk disperses, the restraining force on planetary orbits is removed. The embryos and growing planets are left to interact with each other through pure gravitational dynamics, without the disk's mediating influence. This is where the solar system's final configuration, its actual orbital architecture, gets decided. And it is a process that is far less orderly than the picture of a flat disk might suggest. Computer simulations of the final stages of terrestrial planet formation show a period of chaotic, violent bombardment. Planetary embryos in the inner solar system collide with each other repeatedly. Some are ejected, some are absorbed. The Earth itself is thought to have formed through a series of such collisions, with its final size being determined by the giant impact that also created the Moon. A collision with a Mars-sized body hypothesized to be called Theia, around 4.5 billion years ago. That collision was not a grazing encounter in the perfect midplane of the disk. It was a complex, three-dimensional event, and its geometry is one reason the Earth's axis is tilted at roughly 23.5 degrees, rather than perfectly upright relative to the orbital plane. Stay with this for a moment. The fact that the planets orbit in the same plane does not mean the solar system is a tidy place. The plane is flat. But within that flat plane, the history of construction was deeply violent. Worlds were built by catastrophe. The neatness of the orbital geometry preserves no record of the carnage that produced it. The outer solar system tells an even more dramatic story. Jupiter and Saturn, once they had grown to something approaching their current masses, exerted enormous gravitational influence on the rest of the disk. Uranus and Neptune, it is now thought, did not form where we find them today. The leading model of the solar system's dynamical history, called the Nice model, named after the city of Nice in southern France, where the research group that developed it was based, proposes that the outer planets underwent a period of dramatic orbital migration after the gas disk dispersed. In this model, Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved significantly outward, driven by angular momentum exchanges with a vast population of small icy bodies in the outer solar system. This migration was not a gradual, well-behaved drift. It was an instability. At some point, Jupiter and Saturn reached a resonance, a gravitational coupling where their orbital periods became simple integer multiples of each other, and the system became dynamically chaotic. Uranus and Neptune were scattered outward. The inner solar system was bombarded with debris. The asteroid belt was largely cleared, and the outer solar system was sculpted into roughly its current configuration. What is remarkable, from the perspective of the flatness story, is that this enormous disruption did not significantly scatter the planets out of the disk plane. The migration of the planets happened within the plane, not perpendicular to it. The reason is angular momentum conservation operating again. The total angular momentum of the solar system, the net rotational motion inherited from the original disk, was preserved even through the chaos of the Nice model instability. Individual orbits shifted in size and shape, but the fundamental plane of the system, defined by that conserved angular momentum vector, stayed fixed. The planets were rearranged, but the flat was not undone. This is one of the deepest and most remarkable aspects of the flatness story. The solar system has been through extraordinary dynamical violence, giant impacts, orbital instabilities, planetary migrations, and yet the memory of the original disk's geometry persists in the orbital planes of the planets to this day. Conservation of angular momentum is robust in a way that almost defies intuition. It is not that the system was gently handled and carefully preserved. It is that the physical law governing rotational motion is so fundamental that even chaos cannot erase what it has written. Stop here for a moment. Roughly 400,000 years of collapse have produced the disk. The disk has lasted approximately 10 million years. Planetesimals have formed, grown into embryos, and survived the disk's dispersal. The solar system is now roughly 50 million years old, and the planets are approaching something like their final configuration. The flatness is already there. It was there from the moment the disk formed. The question now is, how precisely flat is it, and what, if anything, disturbs it? The answer begins with a measurement so elegant it deserves its own consideration. The nearly circular mean eccentricity approximately 0.06 and coplanar mean mutual inclination approximately 3 degrees. Orbits of the solar system planets motivated Kant and Laplace to hypothesize that planets are formed in the way that modern planetary science has since confirmed. 3 degrees. The planets of our solar system orbit within about 3 degrees of the same plane, on average. Mercury is the outlier at about 7 degrees from the ecliptic. Venus, Earth, and Jupiter orbit within a degree or two. The system is flat to a degree that strikes any astronomer as extraordinary. But is it unusually flat? That question, for almost the entire history of astronomy, was unanswerable. Because every theory anyone had ever built about why the solar system is flat, Kant's, Laplace's, Safronov's, was based on a sample size of 1, our solar system, the only planetary system humanity had ever seen. Imagine being asked to determine whether human beings are unusually tall, when the only human you have ever met is yourself. You have no comparison. You have no distribution. You have a single data point, and a single data point cannot tell you anything about how typical it is. That changed on a night in October of 1995. 2 Swiss astronomers from the Geneva Observatory, Michel Maillot and Didier Queloz, were using a high-precision spectrograph at the Haute-Provence Observatory in southern France. They pointed a high-precision spectrograph at a star 50 light-years away in the constellation Pegasus. The star is called 51 Pegasi. It is unremarkable. A yellow dwarf, slightly older than the Sun, slightly more massive. The kind of star astronomers had been quietly searching around for years, hoping to find another solar system somewhere out there. What Mayer and Queloz found was not another solar system. It was a single planet. And that planet, according to everything the nebula hypothesis said about how planets should behave, should not have existed at all. The discovery would eventually earn them the Nobel Prize in Physics in 2019. It opened a window onto the architecture of planetary systems that astronomers had never previously had access to. And what they saw through that window was deeply disorienting. The planet orbiting 51 Pegasi was a gas giant, roughly half the mass of Jupiter, completing a full orbit of its star in just over 4 days. 4 days. Jupiter takes nearly 12 years to complete a single orbit of the Sun. A planet of Jupiter's size and mass, sitting at a distance from its star so close that its surface temperature reaches roughly 1,000 degrees Celsius, was something that the solar nebula model had not predicted and could not easily explain. This world, and the dozens of similar worlds found in the years that followed, came to be known as hot Jupiters, and they were only the beginning of the surprises. Here is where the story of orbital flatness becomes genuinely strange. You probably think that if all planetary systems form from spinning disks, they should all be roughly flat, with their planets orbiting in something close to the same plane. The textbook picture says that disk formation is universal, angular momentum conservation is universal, and therefore orbital coplanarity should be universal. That picture is almost entirely insufficient because it ignores what can happen to a planetary system after the disk is gone. But here's what almost nobody tells you about exoplanetary orbital geometry. A substantial fraction of known planetary systems are not flat. Some of them are not even close to flat. And the reasons why illuminate, by contrast, exactly what made our own solar system's orderly flatness possible. The Kepler Space Telescope, launched by NASA in 2009 and operated until 2018, surveyed roughly 150,000 stars in a fixed patch of sky near the constellation Cygnus, watching for the tiny dimming of starlight that occurs when a planet passes in front of its host star. Kepler discovered thousands of planet candidates, and analysis of systems with multiple transiting planets revealed something reassuring about the general tendency of planetary systems. Most multiple planet systems found by Kepler appear to be in nearly coplanar orbits. The Kepler multiples fall on the linear relation of the solar system objects, and they are on similarly circular and coplanar orbits to the solar system planets. For systems with several smaller, rocky or sub-Neptune-sized planets, the flatness appears to be a reliable outcome of disk formation. The physics works the way the theory predicts. The disk forms, the planets form inside it, and the result is a set of nearly coplanar worlds. But then there are the hot Jupiters. And the hot Jupiters tell a radically different story. When astronomers measure the angle between a planet's orbital plane and the equatorial plane of its host star, a quantity called the spin-orbit angle or stellar obliquity, they expect, based on the disk model, to find something close to zero. The disk should be roughly aligned with the star's equator. The planet should form in the disk, and so the planet's orbit should be aligned with the star's spin. For most multi-planet systems, this is what they find. For hot Jupiters, it is not. Rossiter-McLaughlin measurements of the obliquity of hot Jupiter planetary orbits, the angle between the planet orbital axis and the stellar rotation axis, show that highly misaligned configurations are not rare. Not rare. That is the key phrase. More than half of hot Jupiters have orbital planes substantially misaligned with their parent star's rotation. Some orbit at angles of 30 degrees, 60 degrees, even 90 degrees, perpendicular to the star's equatorial plane. Some orbit in the retrograde direction, moving opposite to the star's spin, in apparent violation of everything the nebula hypothesis would predict. The star, WASP-17, located roughly 1,300 light-years from Earth in the constellation Scorpius, hosts a gas giant that orbits in a retrograde direction, opposite to the rotation of its host star. The star WASP-33, located roughly 400 light-years away in the constellation Andromeda, hosts a hot Jupiter in an almost polar orbit, its orbital plane nearly perpendicular to the star's equatorial plane. These are not minor deviations. These are planetary systems that appear to have been fundamentally scrambled. How does a planet end up in a retrograde orbit around its own star? If it formed in a disk, and if disks are aligned with the star's rotation, then the answer cannot be that it simply formed there. Something must have moved it. Something must have taken a planet that began its existence in an orderly, flat disk and transported it to a wildly tilted orbit. And here is where the physics of gravitational dynamics becomes both remarkable and somewhat disturbing. The leading explanation involves a process called the Kozai leadoff mechanism, first described by the Soviet researcher Mikhail Lidov in 1961, and independently by the Japanese astronomer Yoshihide Kozai in 1962. The mechanism operates in three body systems: a central star, an inner planet, and a distant third body. Another planet, a brown dwarf or a binary companion star, on an inclined orbit. When the third body's orbit is sufficiently inclined with respect to the inner planet's orbit, it exerts a gravitational torque that causes the inner planet's orbital inclination and eccentricity to oscillate in a coupled periodic manner. The inclination can grow from small values to very large ones. The eccentricity can grow from nearly circular to nearly radial. The oscillations can drive the inner planet's orbit to extreme eccentricity, bringing it very close to the star during each perihelion passage. Tidal forces from the star then dissipate energy, shrinking and circularizing the orbit. The result is a hot Jupiter, a massive planet on a very short, close orbit that may have ended up in an inclined or even retrograde configuration depending on where in the Kozai leadoff cycle the tidal circularization happened to occur. For a given set of system parameters, a misaligned hot Jupiter is likely to be formed in the presence of a more massive planetary companion within a certain distance of the inner system, with sufficient mutual inclination and eccentricity. This is a profound result. It means that the flatness of a planetary system is not permanently guaranteed by its formation in a flat disk. The flatness can be destroyed by subsequent dynamical evolution, particularly if the system contains a distant massive companion on an inclined orbit. The Kozai leadoff mechanism at present is the leading explanation for how hot Jupiters end up on tilted or retrograde orbits. It fits the most data. It explains the most extreme cases, the perpendicular orbits, the retrograde ones, without requiring exotic initial conditions. For a given set of system parameters, a misaligned hot Jupiter is likely to have been formed through Kozai leadoff oscillations, driven by a more massive companion in the outer system. There are alternative mechanisms that may also be at work in some cases. Planet-planet scattering, a chaotic period of close gravitational encounters between multiple giant planets in a young system, can produce eccentric inclined orbits that are later circularized by tides. Primordial misalignment, the idea that the disk itself was tilted relative to the star's equatorial plane from the very beginning due to chaotic accretion or interactions within the birth cluster of stars, may explain a smaller subset of cases. These mechanisms are not mutually exclusive. Different systems may have arrived at their misaligned architectures through different pathways. But the dominant candidate for the most extreme misalignments observed is Kozai leadoff. And what makes it remarkable is what it implies about our own solar system. It implies that the flatness we inherit from the disk can be undone after the fact by a single distant companion on the wrong orbit. Flatness is not permanent. It is preserved by absence, the absence of the kind of disruptor that would have scrambled it. Our solar system has no close binary companion star, no massive distant body on a steeply inclined orbit, no third party with the gravitational leverage to drive a Kozai leadoff instability in Jupiter or Saturn. That absence is part of why we are flat. Against this background of chaotic and misaligned exoplanetary systems, the near-perfect flatness of our own solar system begins to look less like an inevitable outcome of disk physics and more like a fortunate circumstance. The solar system has no known close binary companion star that could drive a Kozai leadoff instability in the giant planets. The Sun is a single star. Jupiter and Saturn, though they exerted gravitational influence on each other and on the smaller bodies of the solar system, never reached a configuration that sent one of them spiraling inward on a high eccentricity orbit. The nice model instability was violent, but it played out within the plane. The giant planets stayed roughly where they were, and the disk's angular momentum geometry was preserved. One of the most striking pieces of evidence for the relative dynamical calm of our solar system, at least compared to many exoplanetary systems, comes from Kepler-56, a red giant star located some 3,000 light-years from Earth, in the direction of the constellation Cygnus. Kepler-56 hosts at least two inner planets with orbital periods of about 10 and 21 days. And these two planets orbit in a plane that is tilted about 45 degrees away from the star's equatorial plane. They are tilted together, coplanar with each other, but both misaligned with their host star. What the Kepler-56 data show is that tilted planetary orbits happen in systems without hot Jupiters, with torques induced by wide-orbiting companions a possible cause. There is a third, more massive companion in a wide orbit around Kepler-56. And the best current explanation is that this companion's gravitational torque tilted the entire inner planetary system away from the star's equatorial plane after the planets had already formed. The disk's legacy, coplanarity between the planets, is preserved, but the disk's alignment with the star has been lost. This distinction is important. Coplanarity, the condition in which the planets all orbit in the same plane relative to each other, is a more robust property than alignment. The condition in which the planet's shared orbital plane is also aligned with the star's equatorial plane. The planets can be coplanar without being aligned. They can share a flat orbital configuration that has been torqued away from the star's equator as a unit. What Kepler 56 shows us is that the disk's gift of internal coplanarity can survive even when the disk's alignment with the stellar equator has been scrambled. Our solar system, as best we can measure, has both properties. The planets orbit in nearly the same plane, and that plane is very nearly aligned with the Sun's equatorial plane. The Sun's rotational equator is tilted only about 7 degrees from the ecliptic. Both properties, coplanarity and alignment, appear to be intact. This is rarer than the textbook suggests. It is worth pausing on the scale of what has been observed in exoplanetary systems because the contrast with our own solar system is so instructive. Transiting exoplanet host stars exhibit a wide range in their obliquities, from completely aligned, as in the case of HD 189733, to moderately misaligned at around 37 degrees, as with XO3, to perpendicular, as with WASP7, and even retrograde, as with WASP17. Completely aligned, perpendicular, retrograde. The full range of orbital geometries appears to exist in nature. Some systems are as orderly as ours. Some have been catastrophically rearranged. And we are only now, with data from telescopes like Kepler and its successor TESS, and from ground-based spectrographs, using techniques like the Rossiter-McLaughlin effect, beginning to map the distribution of orbital geometries across the galaxy. The Rossiter-McLaughlin effect is worth explaining because it is one of the most elegant measurement techniques in modern astronomy, and because it is our primary tool for understanding spin-orbit alignment in exoplanetary systems. When a planet transits, passes in front of, its host star, it blocks a small fraction of the star's light. But the star is rotating. One side of the star is moving toward us and is blue-shifted, while the other side is moving away and is red-shifted. As the planet crosses the stellar disk, it preferentially blocks light from one side or the other, causing a characteristic asymmetry in the star's spectral line shapes. By measuring this asymmetry as a function of time during the transit, astronomers can determine the projected angle between the planet's orbital plane and the star's rotational equator. It is the same principle that lets you determine which way a spinning top is tilted by watching how it blocks a beam of light. The technique was first proposed theoretically and then applied in the 1990s and 2000s by astronomers, including Simon Albrecht, Joshua Wynne, and their collaborators, transforming our understanding of orbital architectures across the galaxy. The emerging picture, as of the most recent surveys, is something like this. Small, rocky, multi-planet systems tend to be flat and aligned, consistent with having formed quietly in well-behaved disks and experienced little subsequent dynamical violence. Systems dominated by hot Jupiters tend to be misaligned, suggesting that whatever process created the hot Jupiters also scrambled the orbital geometry. And there is a middle category, systems with giant planets at intermediate distances, whose orbital architectures are varied and still being characterized. Our solar system falls into the first category more comfortably than the second. We have giant planets, but they are far from the Sun, They are not hot Jupiters, and their presence has not scrambled the inner system's flat architecture. The giant planets are the dominators of the angular momentum budget, as we discussed, but they are also, in a sense, the guardians of the flatness. Jupiter's enormous gravitational influence stabilizes the orbits of the inner planets against large-scale chaos. Some researchers describe Jupiter as a gravitational shield for the inner solar system, a massive body whose gravity deflects or captures potential impactors and perturbative influences from the outer solar system. Others are more cautious about this characterization, pointing out that Jupiter's gravity can also send objects from the outer solar system into the inner solar system under some circumstances. The debate about whether Jupiter is on net protective or disruptive is ongoing. But from the specific perspective of orbital flatness, the giant planet's role is largely constructive. They were born on the disk. They dominate the angular momentum of the disk, and their orbital memory of the disk's geometry is so strong because their angular momentum is so large that it would take an extraordinary perturbation to tilt them significantly out of the invariable plane. That robustness propagates to the system as a whole. Because the invariable plane is so thoroughly dominated by Jupiter and Saturn, and because Jupiter and Saturn are so massive, the invariable plane is effectively locked. It is not going anywhere. The invariable plane of the solar system, Laplace's invariable plane, is fixed to an extraordinary degree of precision. The invariable plane's orientation over a 100-year interval does not vary more than 1/10 of an arcsecond in inclination. An arcsecond is 1/3600th of a degree. The invariable plane of the solar system wobbles by less than a fraction of a degree over an entire century. It is, for all practical purposes, immovable. It is the closest thing to a perfect, permanent flat surface that the solar system possesses. And it exists because of angular momentum. Because a cold cloud of gas, billions of years ago, happened to have a slight net rotation in one particular direction. Because conservation of angular momentum amplified that rotation as the cloud collapsed. Because the amplified rotation created a disk. Because the disk gave birth to giants. And because the giants remember the disk. That chain of causation, from cold cloud to invariable plane, is what we have been tracing. It is a causal spine that runs through 4.5 billion years of solar system history. And we have now followed it to the point where the disk is gone, the planets are established in their orbits, and the flatness has been locked in by the overwhelming angular momentum dominance of Jupiter and Saturn. But the story is not complete. Because even within a flat system, not all orbits are equally flat. And the deviations from perfect flatness, the inclinations of individual planets, the tilt of Mercury's orbit, the wobble of Pluto's orbital plane, each tell their own sub-story of forces that pushed against the inherited geometry of the disk. Mercury's orbital inclination of about 7 degrees, the largest of any of the 8 planets relative to the ecliptic, is thought to be a consequence of dynamical interactions during the late stages of terrestrial planet formation. Mercury is the innermost planet, and its orbit is also the most eccentric of the 8 planets, with a notably elongated path. Both the inclination and the eccentricity are likely the results of close gravitational encounters with other planetary embryos during the violent final assembly of the inner solar system. The embryo that became Mercury was involved in, or affected by, collisions and near misses that pushed it slightly out of the perfectly flat configuration it would have inherited from the disk. Venus, Earth, and Mars have orbital inclinations of 3.4, 0, and 1.9 degrees, respectively, relative to the ecliptic. These small but non-zero inclinations are the accumulated residuals of the same gravitational dynamics, the violence of final accretion, the long-term gravitational perturbations between the planets, and in some cases, the distant influence of Jupiter and Saturn through secular resonances, gravitational couplings that operate over millions of years and can gradually change the shapes and orientations of orbits. A secular resonance is a subtle but important concept in orbital mechanics. It occurs when the rate at which one planet's orbital ellipse precesses rotates slowly in space, matches the precession rate of another planet's orbit. When two orbits precess at the same rate, they are locked in a resonance, and gravitational interactions between the two planets are coherent rather than averaging out. Over long timescales, this coherence can build up to produce significant changes in orbital elements, including inclination. The asteroid belt, sitting between Mars and Jupiter, preserves the signature of secular resonances in dramatic form. The belt is not uniformly populated. There are gaps. The Kirkwood Gaps, named after the American astronomer Daniel Kirkwood, who identified them in 1866, at specific orbital distances where orbital resonances with Jupiter make orbits unstable. Asteroids that wander into those resonances are gradually driven to high eccentricities and ultimately either collide with a planet, fall into the Sun, or are ejected from the solar system. The belt's patchy structure is a direct record of Jupiter's long-armed gravitational influence, sorting and clearing material over billions of years. The Kuiper Belt, the vast ring of icy bodies beyond Neptune's orbit, stretching from roughly 30 astronomical units to 50 astronomical units from the Sun, also preserves the record of the solar system's dynamical history in its orbital inclinations. The classical Kuiper Belt objects, those with relatively circular orbits that have not been significantly disturbed, have orbital inclinations clustered near the invariable plane, consistent with their origin in a flat disk. But there is also a population of scattered disk objects, Kuiper Belt bodies that were gravitationally deflected by Neptune during the period of planetary migration, with much higher inclinations and eccentricities. The scattered disk objects are the dynamical refugees of the Nice model instability, thrown into their tilted orbits by the chaos of the giant planet rearrangement. Even Pluto, with its orbital inclination of 17 degrees and its eccentric orbit that crosses Neptune's path, bears the signature of this history. Pluto is locked in a resonance with Neptune, a 3-to-2 resonance, meaning Pluto completes 2 orbits for every 3 of Neptune's. That was established during Neptune's outward migration. The resonance protects Pluto from close encounters with Neptune, even though their orbits cross, because they are never actually in the same place at the same time. Pluto is not a rebel from the disk. It is a survivor of the migration, captured into a safe harbor by the same dynamics that scrambled the outer solar system's architecture. The flat disk is the origin. But the detailed structure of the solar system, every deviation from perfect flatness, every inclined orbit, every dynamical family of objects, is the record of what happened after the disk was gone. Pause here, because something important in this story deserves formal acknowledgement. We have traced the path from the molecular cloud to the formation of the protoplanetary disk, from the disk to the growth of planetesimals and planets, from planet formation to the dispersal of the disk and the dynamical evolution of the solar system. The flatness we see today is the preserved geometry of the original disk, maintained by the angular momentum dominance of the 4 giant planets, slightly perturbed by 4.5 billion years of collisions, migrations, and gravitational perturbations, but fundamentally intact. The question that now opens before us is deeper than the mechanism. It is the question of universality. How common is this kind of flatness in the universe? how many planetary systems, orbiting other stars in other corners of the galaxy, end up with the orderly, nearly coplanar architectures that we have in our solar system? And what does the answer to that question mean for the broader question of whether planetary systems like ours, systems capable of producing and sustaining the kind of long-term stability that life requires, are common or rare? Those questions bring us to the edge of what we know. And at that edge, the story changes character. It stops being purely a story about physics and becomes a story about probability, about contingency, and about the particular circumstances that made this solar system, with its particular flatness, possible. Now, those circumstances deserve attention because they are more specific than the general theory of disk formation implies. The solar system formed in a molecular cloud, but molecular clouds are not homogeneous. They are turbulent, structured, clumpy environments with filamentary substructure, embedded clusters of young stars, and significant variations in density and velocity from one region to another. The specific properties of the particular dense core within the molecular cloud that collapsed to form the solar system, its mass, its temperature, its initial rotation rate, its magnetic field strength, the exact direction of its angular momentum vector, were not determined by the general theory. They were set by the specific local conditions in one particular region of one particular molecular cloud, in one particular spiral arm of the Milky Way, roughly 4.5 billion years ago. We cannot know what those specific conditions were. We do not know the initial angular momentum vector of the pre-solar cloud with any precision, and we cannot reconstruct it from observations of the present-day solar system. This is not a temporary gap in our knowledge, the kind that future observations or better models might close. It is a genuine epistemological limit. The conditions in the pre-solar cloud were erased when the cloud collapsed and the disk formed. The disk preserved the net angular momentum direction, but it did not preserve information about where that angular momentum came from or what the detailed structure of the original cloud looked like. We are, in this specific sense, unable ever to fully reconstruct the starting conditions of our solar system's formation from observations of the solar system itself. This is one of several places in the story where the honest answer is not, we do not yet know, but we cannot know. The distinction matters. Not yet knowing suggests that patience and better instruments will eventually provide the answer. Cannot know suggests a fundamental limit, a boundary between the recoverable past and the irrecoverably lost. The initial conditions of the solar system's formation are, in important ways, on the far side of that boundary. What we do know is that the net result of those unknown initial conditions was a solar system with a particular angular momentum vector that produced a disk, and a disk that produced planets, and planets whose orbital geometry we can measure with extraordinary precision today. The measurement exists even if the cause of the measurement's specific value is inaccessible. And the measurement tells us something beautiful. The solar system is flat, not perfectly flat. No real physical system achieves perfection, but flat to a degree that speaks of deep physical law operating over enormous timescales on the most chaotic imaginable starting conditions. Stand outside on a clear night and look for Jupiter. In the northern hemisphere on most clear nights, it is one of the brightest objects in the sky, outshining everything except Venus and the Moon. Now look for Saturn, dimmer but still distinctive. Then find Mars with its reddish tinge. These worlds do not wander freely across the sky. They are constrained, all of them, to a narrow band. They trace a line across the heavens because they are all embedded in the same flat sheet of orbital geometry, a sheet whose existence is a direct consequence of angular momentum conservation in the original pre-solar cloud. You are looking at the fossil of a cloud. You are seeing, in the constrained paths of those bright points of light, the preserved memory of a rotation that began billions of years ago in a darkness far colder than anything on Earth's surface, in a gas cloud so large that light took years to cross it. That rotation, amplified and refined and geometrically locked into place, is what organizes the night sky into a pattern instead of a scatter. It is a pattern that physicists can calculate. It is a pattern that ancient astronomers noticed without understanding the cause. It is a pattern that still surprises anyone who thinks carefully about it, because the starting conditions, chaos, 3 dimensions, turbulence, violence, seem so hostile to the orderly outcome that resulted. The next layer of this story asks, what about the details of the disk itself? We have spoken of the disk in broad terms, as a flat structure of gas and dust within which planets form. But the disk has a structure of its own, a thickness, a temperature gradient, a set of internal physical processes that directly shapes the inclinations of the planetary orbits that emerge from it. Understanding that structure is the next step in the causal chain. Picture yourself floating above the midplane of the protoplanetary disk, roughly 100 million kilometers from the young sun, at a time approximately 4.5 billion years ago. The disk around you is not the kind of flat, featureless sheet that a simple diagram might suggest. It is a living, turbulent, physically complex environment, and its complexity directly shapes the orbital geometry of the worlds that will grow inside it. The disk has a vertical structure. At the midplane, the geometric center of the disk's thickness, the density of gas and dust is at its maximum. Conditions here are dense enough that the gas is nearly opaque to radiation, creating a region of elevated temperature and pressure at the disk's equatorial waist. Moving upward away from the midplane, the density falls off steeply. The outer layers of the disk are more transparent, cooler, and directly illuminated by the young sun's radiation. The disk is, in cross-section, something like a lens, thicker at the edges than at the center, flaring outward as you move away from the sun. This flared structure is not incidental. It is a direct consequence of the same pressure support that keeps gas distributed vertically, even as gravity pulls it toward the midplane. The scale height of the disk, the vertical distance over which the gas density drops by a factor of roughly 2.7, increases with distance from the sun because the temperature falls off more slowly with radius than gravity does. The outer regions of the disk are comparatively puffy, while the inner regions are thin and dense. This structure has been confirmed directly by observations of edge-on protoplanetary disks, where astronomers can see the disk's cross-sectional shape silhouetted against background light. Such observations confirm that large millimeter-sized grains are subject to significant vertical settling in protoplanetary disks, while the gas remains extended vertically over a much larger scale. The dust and the gas behave differently in this vertical structure, and that differential behavior is directly relevant to planet formation and orbital flatness. Dust settles toward the midplane under the pull of the disk's vertical component of the sun's gravity, while gas pressure keeps the gas more vertically extended. As we noted earlier, this creates a thin, dense sublayer of dust at the midplane, the environment where planetesimals form and where the earliest seeds of planets first assemble. The midplane is where flatness is born, but the disk is not static. It rotates differentially. The inner parts rotate faster than the outer parts, following Kepler's laws. This differential rotation creates shear, and shear drives turbulence. The turbulence stirs the disk vertically, puffing it up and competing with the gravitational settling of dust. The balance between settling and turbulence determines how thin the dust sublayer at the midplane actually is, and therefore how efficiently the streaming instability and other concentration mechanisms can operate to form planetesimals. Here is a complication that is worth dwelling on. The turbulence in the protoplanetary disk is not random and uniform. It is structured and driven by specific physical mechanisms, and the nature of that turbulence is one of the genuinely uncertain aspects of disk physics. The dominant candidate mechanism for generating turbulence in protoplanetary disks is the magnetorotational instability, first worked out theoretically by Stephen Balbus and John Hawley in 1991. The magnetorotational instability works as follows. A weak magnetic field threads the disk, coupling adjacent layers of gas that are rotating at slightly different speeds. The magnetic tension between these layers acts like a spring. The inner layer is moving faster than the outer layer, and the magnetic coupling transfers angular momentum from the inner layer to the outer layer, causing the inner layer to slow down and fall inward while the outer layer speeds up and moves outward. This is exactly the angular momentum transport that the disk needs to allow material to accrete onto the growing star. But it is also a source of turbulence because the process is unstable. The initial perturbation grows rather than damping. Magnetorotational instability is an elegant piece of physics, but its operation in protoplanetary disks depends on the gas being sufficiently ionized to couple to the magnetic field. In the cold, dense regions of the disk midplane, precisely where planet formation is happening, the gas may not be ionized enough for the mechanism to operate efficiently. This creates what researchers call dead zones, regions of the disk where turbulence is suppressed, where the disk is laminar rather than turbulent, and where dust settling can proceed more efficiently. Some researchers think that these dead zones are actually crucial for planetesimal formation, because the reduced turbulence allows the dust sublayer to become dense enough for the streaming instability to operate. Others point out that even a small amount of turbulence can disrupt planetesimal formation. The angular momentum transport problem, the question of how mass flows inward through the disk while angular momentum flows outward, is directly connected to the turbulence problem, and it remains one of the most active areas of theoretical and observational research in planet formation. Angular momentum transport can be of hydrodynamic and magnetic origin. The turbulent viscosity is thought to be responsible for the transport of mass to the central protostar and angular momentum to the periphery of the disk. Paleomagnetic measurements of ancient meteorites, rocks that formed in the early solar system and have preserved a record of the magnetic field they experienced during formation, provide some of our most direct evidence about the magnetic environment of the early solar disk. These measurements indicate the presence of magnetic fields of a certain intensity at distances of roughly 1 to 3 astronomical units from the Sun during the disk's active phase, consistent with the predictions of models in which magnetism played a central role in mass transport. The magnetic field strengths inferred from meteorite paleomagnetism are consistent with those predicted to enable typical astronomically observed protostellar accretion rates. This is remarkable. Tiny rocks that fell to Earth as meteorites, sitting in museum collections and laboratory drawers, carry within them a magnetic memory of the field environment of the protoplanetary disk 4.5 billion years ago. They are, in a very literal sense, fossil records of the disk's physics. The disk's thermal structure is equally important for the flatness story, particularly through its role in determining where different types of planets form. We discussed the ice line, the boundary beyond which volatile compounds can exist in solid form. But the disk's thermal evolution over time is more complex than a simple static temperature gradient. As the disk accretes material onto the forming sun, as the Sun's luminosity changes and as the disk itself cools and thins over millions of years, the ice line moves inward. Early in the disk's lifetime, when accretion rates are high and the disk is hot and luminous, the ice line may have been as far as 10 or 15 astronomical units from the Sun. Later, as the disk cooled, it moved inward to its final position at roughly 2 to 3 astronomical units. This migration of the ice line has significant consequences for the formation of the giant planets. Jupiter is thought to have formed when its solid core, having grown massive enough, initiated rapid gas accretion from the surrounding disk. The timing of this event relative to the ice line's position determined how much solid material was available for Jupiter's core to accrete, and therefore how quickly Jupiter grew. Some models suggest that Jupiter's core formed near the ice line, where the concentration of solid material was highest due to the enhanced availability of ice. Others place it further out. The exact birth location of Jupiter is actively debated, and its subsequent inward migration to approximately its current position is part of the grand picture of the NICE model. What matters for the flatness story is that Jupiter, wherever it formed, grew within the disk. It was confined to the disk plane during its formative phase, and its orbital memory of that confinement is what ultimately determines the invariable plane of the solar system today. Now we encounter another place where the simple version of the picture breaks down. Everyone knows that the solar system's planets orbit in nearly the same plane as the Sun's equator. The textbook picture shows a tidy flat disk with the Sun at the center and everything nicely aligned. You probably think this means the Sun's rotational equator and the planetary orbital plane are the same thing, that they are locked together by the physics of formation. But here's what almost nobody tells you. The Sun's equatorial plane is tilted by about 6 degrees relative to the invariable plane of the solar system. The Sun, the very object at the center of the system, is slightly misaligned with the plane defined by its own planet's angular momentum. 7 degrees is not a large angle by the standards of exoplanetary misalignment. It is nothing like the 40-degree tilts seen in systems like Kepler-56 or the retrograde orbits of some hot Jupiters. But it is measurably non-zero, and its non-zero value demands explanation. Several competing explanations have been proposed. One idea is that the Sun's rotation axis was originally well aligned with the disk's angular momentum, but was subsequently tilted by gravitational torques from passing stars during the first billion years of the solar system's history, when the Sun was still embedded in its birth cluster of young stars. In the dense environment of a stellar birth cluster, close stellar encounters can deliver gravitational kicks to a planetary system's orbital geometry, gradually shifting the alignment between the stellar rotation axis and the disk midplane. Another proposal, developed in part by Konstantin Batygin and his collaborators at the California Institute of Technology, suggests that a hypothetical distant ninth planet, a large body, perhaps 10 times the mass of Earth, orbiting the Sun at hundreds of astronomical units in an inclined orbit, has been gradually tilting the orbital planes of the known planets relative to the Sun's equator over the age of the solar system. In this model, the Sun's equator has remained stable, but the planet's orbital planes have been slowly precessing under the torque of the distant unseen world, creating the apparent tilt. This is one of several motivations for the ongoing search for what researchers call Planet 9. Though, as of this writing, no direct observational confirmation of such a body has been found, and the question of whether it exists remains genuinely open. A third explanation suggests that the misalignment is simply a relic of the original formation process, that the pre-solar cloud core had an angular momentum vector that was not perfectly aligned with the Sun's eventual rotation axis, perhaps because of turbulent fluctuations in the cloud or because of asymmetric accretion during the star's earliest formation phase. In this view, a 7-degree misalignment is not surprising. It is simply the residual of the messy business of star formation. Some researchers think the birth cluster explanation is most likely. Others favor the primordial misalignment hypothesis. Still others maintain interest in Planet 9. We do not know which explanation is correct, and we cannot rule out that all three mechanisms contributed to some degree. The 7-degree tilt of the Sun is one of the smaller mysteries in the solar system's flatness story, but it is a genuine mystery, and it serves as a reminder that even our well-studied, carefully mapped local neighborhood still holds questions that have not been fully answered. This is worth pausing on. The solar system is the best observed planetary system in the universe by an enormous margin. We have sent spacecraft to every major body in it. We have landed on the Moon, Mars, Venus, Saturn's moon Titan, several asteroids, and a comet nucleus. We have measured the gravitational fields, magnetic fields, and atmospheric compositions of all 8 planets to extraordinary precision. We have observations of the solar system that span centuries of recorded astronomical measurement. And yet, the 7-degree tilt of the Sun's equatorial plane relative to its own planetary system remains an open question. The explanation is uncertain. That should give us genuine humility about how much we understand of even the most familiar cosmic environment. The solar system is an enormously complex dynamical system that has been evolving for 4.5 billion years, and the observational record we have of it, impressive as it is, covers only a vanishingly small fraction of that history. With that humility in mind, we can look more carefully at what the disk physics tells us about the detailed flatness of the planets, and then expand outward to consider what modern observations of protoplanetary disks around other young stars have revealed. The Atacama Large Millimeter Array, known universally in astronomy as ALMA, is a radio telescope located on the Chajnantor Plateau in the Atacama Desert in northern Chile, at an altitude of roughly 5,000 meters. It consists of 66 high-precision antennas that work together as a single interferometer, giving it angular resolution comparable to what would be achieved by a telescope with a dish diameter of up to 16 kilometers. ALMA became fully operational in 2013, and in the years since, it has fundamentally transformed our understanding of protoplanetary disk structure. The first and perhaps most dramatic result from ALMA regarding protoplanetary disks was the 2014 image of the disk around the young star HL Tauri, located approximately 450 light-years from Earth in the Taurus Auriga star-forming region. HL Tauri is less than 1 million years old, an infant by astronomical standards. And yet, the ALMA image showed its protoplanetary disk as a series of concentric bright rings and dark gaps, structures that many astronomers had not expected to see at such an early stage of the disk's evolution. The rings and gaps are now interpreted as evidence of planet formation already underway in a disk that has barely had time to form. Planets, or at least the pressure perturbations caused by forming planets, were apparently already structuring the disk within the first 1 million years of the system's history. These ring structures are flat. They are perfectly, extraordinarily flat. Disks of gas and dust that are thin enough, relative to their radial extent, to be described as two-dimensional to a very good approximation. The millimeter continuum emission in edge-on disks is more compact than the scattered light, both in the vertical and radial directions, and at least 3 disks are consistent with a small millimeter dust scale height of only a few astronomical units, measured at 100 astronomical units radius. A disk that is a few astronomical units thick at a radius of 100 astronomical units has an aspect ratio of a few percent at most. Imagine a compact disk, about 12 centimeters in diameter, but only the thickness of a sheet of paper. That is the proportional geometry of a protoplanetary disk. The flatness is not just a qualitative description. It is a quantitative fact, measured and verified by direct observation of disks around young stars in our galaxy. ALMA observations have also revealed something unexpected. Protoplanetary disks can be warped. A warped disk is one in which the disk's plane is not constant with radius. The inner part of the disk might be oriented differently from the outer part, with a gradual twist connecting the two. Warped disks have been observed around several young stars, and their existence raises important questions about the conditions under which a disk can maintain flatness throughout its radial extent. One source of disk warping is a misalignment between the disk's angular momentum vector and the gravitational field of the central star or of companion objects. In a binary star system, for example, the gravitational influence of the companion can torque the disk, causing it to precess. If the disk is not perfectly rigid, and no real disk is, different radii will precess at different rates, causing differential precession that can produce a warp. The inner parts of the disk, closer to the central star, feel the tidal influence of the companion more strongly and precess faster, while the outer parts precess more slowly. The result is a disk that is twisted, like a broad, flat ribbon that has been given a slow spiral. For a forming planetary system in a warped disk, the implications for orbital flatness could in principle be significant. Planets forming at different radii in a warped disk would inherit different orbital inclinations, because the midplane they form in is not a single consistent plane throughout the disk. They could end up in orbits that diverge from each other in inclination as a function of their distance from the central star. But here is the complication. Observations suggest that disk warping, while real, is not particularly extreme in most protoplanetary disks around single stars. Large disks, routinely observed in many star-forming regions, such as the Orion Nebula, show structures consistent with relatively flat morphology. For isolated star disk systems, the disk's self-gravity and internal pressure tend to maintain flatness against moderate perturbations. Strong warping tends to require either a close companion star or an external perturbation of unusual severity. Our Sun, as a single star without a close binary companion, probably hosted a disk that was relatively flat throughout its extent. Not perfectly flat, but flat enough that the planets forming at different radii inherited very similar orbital inclinations. The Orion Nebula is a particularly instructive place to look at disk formation in the context of an external environment. Located roughly 1,300 light-years from Earth, in the constellation Orion, it is the nearest large star-forming region to the solar system, and it is currently producing hundreds of young stars along with their protoplanetary disks. The Orion Nebula hosts the Trapezium cluster, a tight group of 4 very massive luminous stars whose ultraviolet radiation illuminates the nebula and also photoevaporates the disks of young stars nearby. The disks of young stars in the central region of the Orion Nebula, called proplids, short for protoplanetary disks, when seen as silhouettes against the nebula background, are being actively sculpted by the intense radiation environment. External photoevaporation by the trapezium stars removes material from the outer edges of the disks, potentially truncating them and reducing the total mass available for planet formation. Whether the solar system formed in an environment like the Orion Nebula or in a quieter, less irradiated region of its birth molecular cloud is not known with certainty. Some isotopic evidence in meteorites, specifically certain ratios of radioactive isotopes that were present in the early solar system, suggests that a nearby supernova injected fresh nucleosynthetic material into the pre-solar cloud shortly before its collapse, implying that the Sun's birth environment may have included at least one massive nearby star. If so, the early solar disk may have experienced some degree of external UV irradiation. But the available evidence does not place the Sun in an environment as extreme as the central Orion Nebula. The birth cluster of the Sun was probably a moderately rich cluster, but not one in which the disk was severely truncated or distorted by external radiation. The environment of disk formation matters for flatness in another way, through the stellar density of the birth cluster. In a dense stellar cluster, passing stars can interact gravitationally with a forming planetary system, delivering tidal perturbations that can tilt the disk or the orbits of forming planets. If a star passes close enough, its gravitational influence can truncate the disk, truncate the range of orbital radii at which planets form, and introduce inclinations into the system's architecture. The probability and severity of such encounters depends on the stellar density of the birth cluster and the duration of the cluster's coherence before it disperses. Most young star clusters disperse within the first 100 million years of their star's lives, as stellar winds and radiation from the most massive members gradually unbind the cluster's gravitational cohesion. By the time the planets in a forming system are approaching their final configurations, the birth cluster has likely already dissolved, and the probability of a disruptive stellar encounter has dropped to near zero. The solar system's planets were essentially in their final orbital configuration by the time the birth cluster of the Sun had dispersed, which means that whatever perturbations the cluster environment delivered to the solar system happened early, during the disk phase, when the disk's self-restoring forces were still active, rather than late. The disk would have damped out moderate perturbations during this phase. Severe perturbations, a truly close stellar encounter, would have been catastrophic, but the probability of such an encounter in a typical stellar cluster is small. We were, in this sense, probably lucky, or at least not unlucky. The solar system formed in an environment that was rich enough to supply heavy elements through nearby supernova enrichment, but calm enough to allow the disk to evolve undisturbed for the millions of years needed to form planets. That combination, enriched but not disrupted, may be more common than extreme environments like the Orion Nebula's center, but it is not universal. The story of the protoplanetary disk and the conditions within it that produced the flat solar system we inhabit thus contains both the inevitable and the contingent. The inevitable part is the physics. Angular momentum conservation guarantees that a rotating, collapsing cloud produces a disk, and a disk guarantees that planets form in a plane. The contingent part is the specifics. The particular initial conditions of the pre-solar cloud, the particular environment of the solar birth cluster, the particular sequence of events during the disk's evolution, all of these shaped the specific degree of flatness we observe today. There is one more layer of the disk's physics that deserves attention before we move on, and it concerns what happens not just inside the disk, but at its edges and in its interaction with the forming star. The process of disk dispersal, the mechanism by which the disk is eventually destroyed, ending its influence on the forming planetary system, is directly relevant to the final configuration of planetary orbits. Disks disperse through several mechanisms operating simultaneously. Viscous accretion flows material inward onto the growing star, while simultaneously spreading the outer disk outward to larger radii, redistributing mass and angular momentum. Photoevaporation by the star's own ultraviolet and X-ray radiation heats the disk surface, driving a thermally driven wind that carries gas off the disk at a rate that increases with time as the disk becomes less opaque. The main processes responsible for the disappearance of the gas in disks are viscous diffusion and photoevaporation. A critical transition occurs when the photoevaporation rate catches up to the accretion rate. At that point, the disk can no longer replenish material at the rate it is being lost, and it begins to clear rapidly from the inside out. Once the inner disk is cleared, the star's radiation has direct access to the outer disk, and photoevaporation accelerates dramatically, clearing the disk on a timescale of roughly 100,000 years. This inside-out clearing of the disk has an important consequence for planetary orbits. As the disk disperses from the inside, the torques that have been acting to maintain planetary orbits in the disk plane are gradually withdrawn from the innermost planets first. The outer planets, still embedded in the remaining outer disk, continue to have their orbital inclinations damped, but the inner planets, no longer embedded in gas, are free to evolve under purely gravitational forces, which can include mutual perturbations that gradually excite orbital inclinations. This is one mechanism by which the terrestrial planets, particularly Mercury, with its 7-degree inclination, may have acquired their non-zero orbital inclinations during the final stages of planet formation. The disk dispersed before their orbital inclinations were fully damped to zero, leaving them with residual inclinations that reflect the specific dynamical state. At the moment, the disk withdrew its influence. The disk is both the origin of flatness and, in its dispersal, a partial undoer of the precision of that flatness. It creates the plane, and then, by disappearing, allows small deviations from that plane to persist and grow. What remains after the disk is gone is the gravitational architecture of the planets themselves, their mutual interactions, their resonances, their long-term secular evolution, and the Sun's gravity, which maintains the general orbital structure without actively constraining orbital inclinations. The solar system we have today is the product of 4.5 billion years of this purely gravitational evolution, operating on a starting configuration that was itself the product of the disk's physics. The flatness is, in the end, an inheritance from the disk, which was itself an inheritance from the angular momentum of the pre-solar cloud, which was itself an inheritance from the large-scale structure and dynamics of the molecular cloud in which the Sun was born. The chain runs back through 4.5 billion years to a cold, dark cloud in a galaxy that was already 8 billion years old when the Sun formed. And the geometry of that cloud, its net rotation, the direction of that rotation, is still visible in the night sky every time you watch a planet trace its path through the constellations. Take a moment to look back at the path. We have now traced the story from its origin, a molecular cloud with residual rotation, collapsing under its own gravity, amplifying that rotation through conservation of angular momentum, producing a disk, and sustaining that disk for 10 million years while planets grew within it. The planets inherited the disk's geometry. The disk is gone. The geometry persists. We have examined the detailed physics of the disk, the role of turbulence and magnetic fields, the evidence from meteorite paleomagnetism, the observations from ALMA of protoplanetary disks around other young stars, and the comparison between our solar system's flatness and the extraordinary variety of orbital architectures found in exoplanetary systems. Now we go deeper into the question of what exactly preserves the flatness over time. Not during the disk phase, when active physical mechanisms are operating, but across 4.5 billion years of purely gravitational evolution. What keeps the planets from wandering out of the plane? And what does the answer reveal about the nature of orbital stability itself? The answer begins with a concept called secular dynamics, the long-term, slow evolution of orbital parameters under mutual gravitational perturbations averaged over many orbital periods. This is distinct from the resonance dynamics we have already touched on, which involve commensurability between orbital periods. Secular dynamics does not require any particular ratio between orbital periods. It is simply the cumulative effect of the slow gravitational tugging that planets exert on each other's orbital ellipses over millions and billions of years. Here is the key thing to understand about secular dynamics and orbital inclination. The solar system is not in a state of perfect equilibrium with respect to inclination. The planets are constantly tugging at each other's orbital planes, causing those planes to precess, to rotate slowly in space like the wobble of a spinning top, and causing the inclinations to oscillate slowly back and forth. These oscillations are slow, typical periods of hundreds of thousands to millions of years. But they are real, they are measurable, and they are ongoing right now. The orbital inclinations of the planets are not fixed values. They are dynamic quantities, changing slowly over geological timescales. But here is what makes the solar system stable. These oscillations are bounded. The inclinations oscillate, but they oscillate around small mean values. They do not grow without bound. The total angular momentum of the system, the summed rotational motion of all the planets, which is conserved by Newtonian mechanics, constrains the range of inclination variations. When one planet's inclination increases, the inclinations of other planets must adjust to compensate, because the total angular momentum vector must remain constant in direction and magnitude. The system oscillates collectively, like a set of coupled pendulums, rather than any single planet wandering independently. This collective behavior is what makes the invariable plane meaningful as a long-term reference. The individual orbital planes of the planets precess and oscillate, but their weighted average, the invariable plane, remains fixed. The invariable plane is the center of gravity of the system's angular momentum, and it does not move. There is a deeper result here that is worth stating carefully. The stability of the solar system, the fact that the planets have maintained their current orbital architecture for billions of years without any planet being ejected or colliding with another, is not obvious from first principles. For most of its history, planetary science assumed the solar system was stable simply because we exist to observe it. If it had been catastrophically unstable, we would not be here to ask the question. But this reasoning is circular, and it does not tell us anything about the system's future. In the 1980s and 1990s, numerical simulations of the solar system's long-term evolution began to reveal something unsettling. Jacques Lascar, a French mathematician at the Paris Observatory, performed detailed simulations of the solar system's evolution over hundreds of millions and billions of years, incorporating the secular perturbations between all the major planets. Lascar's results, published in 1989 and refined in subsequent work, showed that the solar system is chaotic on timescales of tens of millions of years. Not chaotic in the sense of unstable. The planets are not going to collide or be ejected on any timescale relevant to human civilization. But chaotic in the precise mathematical sense. Small differences in initial conditions grow exponentially over time, making it impossible to predict the exact orbital configuration of the planets more than about 100 million years into the future. The source of this chaos is primarily the interaction between Mercury and Jupiter through a secular resonance, a coupling between the precession rate of Mercury's orbital ellipse and a resonance frequency of Jupiter's gravitational influence. This coupling can, over hundreds of millions of years, drive Mercury's orbital eccentricity to very high values. In some simulations, Mercury's eccentricity grows large enough that its orbit crosses Venus's orbit, leading to a close encounter, a dramatic destabilization of the inner solar system, and potentially a collision. The probability of this happening within the remaining lifetime of the Sun has been estimated at roughly 1%. 1%. That is not negligible. It means that the solar system, despite 4.5 billion years of apparent stability, is not guaranteed to maintain its current architecture for the next 5 billion years. The flatness, the orbital geometry we have been tracing since the molecular cloud, is stable on human timescales, on civilizational timescales, even on the timescale of complex life on Earth. But it is not eternal. It is a long-lived but ultimately temporary configuration, maintained by approximate conservation laws and bounded oscillations, with a small but non-zero probability of dramatic disruption over cosmic timescales. This is the kind of fact that changes how you think about the solar system, not as a permanent architected structure, but as a long-lived metastable configuration, a dynamical state that has persisted for billions of years and will persist for billions more, but which is not immune to the slow, patient accumulation of gravitational perturbations over truly vast timescales. The flatness we see tonight is real. The planets really do orbit in nearly the same plane. The invariable plane really is essentially fixed on all timescales relevant to human experience. But these are facts about the present-day solar system as it exists now, not eternal truths about the universe. The flatness is preserved by physics, but physics operates on timescales that dwarf human comprehension, and over those timescales, even the most stable-looking configurations eventually yield to the subtle mathematics of chaos. Something here deserves attention: the way in which the same physics that created the flatness also contains the seeds of its eventual disruption. Angular momentum conservation created the disk. The disk created the planets. The planets, interacting gravitationally with each other, create the secular perturbations that drive the slow chaotic evolution of the system. The creator of the order and the source of its eventual dissolution are the same force: gravity operating on rotating matter. Now we move to a scale that we have not yet considered in detail. We have looked at the solar system from the inside, from the perspective of the physics operating within it. Now we step back and look from outside at the solar system as one example among the billions of planetary systems in the Milky Way, and ask, how does the flatness of our system compare to the broader population of planetary systems in the galaxy? The Kepler mission's legacy data, representing thousands of confirmed planets and thousands more candidates, provides the broadest available statistical view of planetary system architectures. The picture that emerges from this data is one of remarkable diversity. Planetary systems come in an enormous variety of configurations: systems with hot Jupiters and nothing else detectable, systems with closely packed super-Earths all orbiting within the distance of Mercury, systems with giant planets on highly eccentric orbits, and systems like ours with a mixture of terrestrial and giant planets in more widely separated, nearly circular orbits. Within this diversity, the coplanarity of multi-planet systems stands out as a relatively common property, at least for the smaller planet systems that make up the majority of Kepler detections. About half of the Kepler planets are in systems with multiple transiting planets, and on average they are on nearly coplanar orbits, similar to those in the solar system. This is consistent with the general prediction of disk formation theory. Planets that form in the same disk should inherit similar orbital inclinations. The fact that Kepler multi-planet systems are generally flat confirms that the physics we have been tracing, from collapsing cloud to spinning disk to planetary orbits, is operating throughout the galaxy, not just in our particular corner of it, But there is a subtlety in the Kepler data that deserves careful attention. The transit detection method, the technique Kepler used to find planets, has a geometric bias toward detecting coplanar systems. If a planetary system has multiple planets, and those planets all orbit in roughly the same plane, then the probability of seeing multiple transits from Earth's vantage point is much higher than if the planets are in randomly oriented planes. A system with planets in wildly different orbital planes would show at most one transiting planet to any given observer, regardless of how many planets it actually contains. This means that Kepler is more likely to find coplanar systems simply because they produce multiple transit signals that are easier to identify and confirm. The implication is that the apparent prevalence of coplanar systems in the Kepler data may be partly a selection effect, rather than a pure measure of how common coplanarity actually is. The true distribution of orbital architectures, the actual fraction of planetary systems that are flat versus those that are tilted, requires statistical corrections for this geometric bias, and those corrections are uncertain. Some researchers have performed these statistical corrections and concluded that the underlying population of planetary systems is indeed generally flat for small planet systems, with the Kepler data providing a broadly representative sample. Others argue that the correction factors are large enough that the true population might be significantly less coplanar than the Kepler sample suggests, with many single transiting planet systems actually being multi-planet systems seen edge-on or at unfavorable angles. The debate is ongoing, and definitive resolution will likely require methods that do not depend on transit geometry, such as astrometry, which measures the tiny wobbles in a star's position caused by the gravitational influence of orbiting planets, and which does not have the same geometric biases as the transit method. The Gaia Space Telescope, operated by the European Space Agency and launched in 2013, is conducting an extraordinarily precise astrometric survey of more than 1 billion stars in the Milky Way. Its measurements of stellar positions and motions, refined over successive data releases, are expected to yield a large catalogue of planetary systems detected by astrometry within the coming years. This catalogue will, for the first time, provide a sample of planetary systems whose detection is not strongly biased toward coplanar configurations, allowing a more robust statistical assessment of how common flat multi-planet systems actually are in the broader galaxy. This is one of the active frontiers of planetary science, and it is genuinely open. We do not yet have a complete picture of the distribution of orbital flatness across the galaxy's planetary systems. We have strong evidence from Kepler that flat systems are common. We have strong evidence from the hot Jupiter population and from systems like Kepler-56 that dramatically tilted systems also exist. We have theoretical reasons to expect that disk physics should generally produce flat systems, while subsequent dynamical evolution, particularly in the presence of massive perturbers, binary companions, or dynamically chaotic epochs, can disrupt that flatness. But the precise relative frequencies of flat versus tilted systems and the precise range of conditions under which flatness is preserved versus destroyed remain active areas of research. What we can say with confidence is that the solar system's orbital flatness is not miraculous. It is the expected outcome of the physics of disk formation, operating in a reasonably favorable environment. But neither is it inevitable or universal. It is a probable outcome of common physics, tempered by specific initial conditions, and a history that, by comparison with the most disrupted planetary systems we observe, appears to have been relatively calm. Here is where the evidence cascade reaches a point that demands reflection before we go further. We have assembled, step by step, the causal chain that explains the flatness of the solar system. We began with conservation of angular momentum in a collapsing molecular cloud. We followed the formation of the protoplanetary disk, the settling of dust to the midplane, the growth of planetesimals, the formation of planets, the dispersal of the disk, and the long-term gravitational evolution of the planetary system. We have compared our solar system to the broader population of known planetary systems and found that flatness is common but not universal, robust but not guaranteed. At each step, we have encountered genuine uncertainties, places where the physics is understood in broad outline, but the details remain contested, where our observational record is incomplete, or where the fundamental epistemological limits of reconstructing the past make complete knowledge impossible. The formation of planetesimals from dust remains incompletely understood. The mechanism of angular momentum transport within the protoplanetary disk, whether through turbulence, magnetic braking, or other processes, is not definitively settled. The 7-degree tilt of the Sun's equatorial plane relative to its planetary system has multiple candidate explanations and no confirmed one. The long-term dynamical stability of the solar system is characterized by chaos rather than determinism, with a small but real probability of catastrophic disruption over billion-year timescales. The distribution of orbital architectures across the galactic population of planetary systems is not yet fully characterized. These are not failures of science. They are the actual frontiers of human knowledge about one of the most fundamental questions in planetary science: how the architecture of a solar system is determined and how that architecture is preserved over time. And here is the paradigm shift, the reframing that changes how everything we have discussed so far looks. We began with a question about geometry. Why do the planets orbit in the same plane? The answer, we have found, is not primarily a geometric answer. It is a thermodynamic answer. The flatness of the solar system is the result of a physical system dissipating energy while conserving angular momentum. The random, chaotic, three-dimensional motion of gas in the pre-solar cloud contained two types of motion: a random component, which could be dissipated through collisions, and a net rotational component, which could not be dissipated because it was conserved. The disk is what remains after all the dissipatable energy has been dissipated. It is the minimum energy configuration consistent with the conserved angular momentum. The solar system is flat because it could not be anything else, not because the starting conditions were specially arranged to produce a flat outcome. Not because some external force imposed flatness on a chaotic system, but because the laws of thermodynamics and angular momentum conservation together drive any rotating, collapsing cloud inevitably toward a disk, toward the flattest possible configuration that still contains all the conserved rotational motion. Flatness is the end state of energy dissipation in a rotating system. This reframes everything. The question was never really, why are the planets in the same plane, in the sense of what forced them to be? The question is better understood as, why would they ever be in any other configuration? What would have to be true for the physics to produce something other than a flat disk? And the answer is, you would need either no rotation at all in the original cloud, which is impossible because nothing in the universe is perfectly motionless, or you would need a subsequent disruption powerful enough to erase the disk's legacy, which requires extraordinary circumstances. The default outcome of planet formation around a single star, absent dramatic disruption, is a flat system. Flatness is not a remarkable thing. Flatness is the inevitable thing. What would be remarkable is a planetary system that managed to stay dramatically non-flat, despite forming around a single, relatively isolated star. That system would require a special explanation. Our flat solar system does not. How many planetary systems form in the galaxy each year? The rate of star formation in the Milky Way is roughly 1 to 3 new stars per year, and the fraction of those stars that form planetary systems appears, from the Kepler and other survey data, to be very high. Likely more than half of all Sun-like stars have at least one planet. Some estimates suggest the Milky Way contains more than 1 trillion planets. Each of those planetary systems began as a rotating cloud. Each of those rotating clouds produced a disk. Each of those disks, in the absence of dramatic disruption, produced a flat planetary system. Flatness is not a specialty of the solar system. It is the galaxy's default mode of planet building. And yet, each of those flat systems is flat in its own specific way. The precise inclinations of the individual planets, the exact orientation of the invariable plane, the degree to which the star's equatorial plane is aligned with the planetary plane. All of these details differ from system to system, reflecting the specific initial conditions of each system's formation and the specific history of each system's dynamical evolution. The flatness is universal. The specific flat is unique. This is a beautiful distinction that is easy to miss. The law that produces flat planetary systems, conservation of angular momentum, is the same everywhere in the universe. It operates in every molecular cloud, in every collapsing core, in every forming disk. But the specific direction in which each system is flat, the specific degree of flatness, the specific architecture of the planets within the flat, these are contingent on history. They are the specific solutions, in specific initial conditions, to a universal equation. The Milky Way galaxy contains billions of flat planetary systems, each one an expression of the same underlying physics, each one oriented in a different direction in space, each one carrying within its orbital geometry a unique record of the specific molecular cloud core from which it formed. Now let's talk about the implications of this framing for the question of life and habitability. We have traced the flatness of the solar system from its origin in the pre-solar cloud to its preservation over billions of years. We have established that flatness is the expected outcome of disk formation physics, that it is robust against moderate perturbations, and that it is common throughout the galaxy. What we have not yet asked is, does flatness matter for life? Is the near-perfect coplanarity of the solar system relevant to the fact that complex life exists here? The answer, surprisingly, is probably yes, but not in the most obvious way. The most direct way in which orbital flatness affects habitability is through orbital stability. A planet that resides in a flat, nearly circular orbit around its star experiences a relatively constant level of stellar irradiation over the course of its year. The seasons are driven by axial tilt, not by variations in the planet's distance from the star. A planet in a highly eccentric orbit, brought about, for example, by the same kind of gravitational scattering that produces hot Jupiters, experiences wildly varying stellar irradiation over the course of its year, potentially freezing and baking in alternation in ways that make the development and sustenance of complex life far more challenging. The Earth's orbital eccentricity is currently only about 1 7/10. The Earth's orbit is very nearly circular, varying in distance from the Sun by only about 3% between perihelion and aphelion. This near circularity is a consequence of the same dynamics that preserve the flatness. The system's angular momentum is too large, and the perturbations from other planets too modest to have driven the Earth's orbit to high eccentricity. The stability of the Earth's orbit, both its inclination and its eccentricity, over billions of years, has provided the long-term climatic stability that complex life on Earth required. A second connection between flatness and habitability is more subtle. The flat architecture of the solar system concentrates the planets in a thin disk, which means that the gravitational interactions between them are long-range and systematic, rather than random and chaotic. This systematicity produces the kind of bounded secular oscillations we discussed earlier. Slow, predictable oscillations rather than chaotic wandering. The Earth's axial tilt, for example, is stabilized over long timescales primarily by the gravitational influence of the Moon, but also in part by the secular dynamics of the solar system operating in its flat, organized configuration. The famous Milankovitch cycles, periodic variations in the Earth's orbital parameters that drive long-term climate oscillations and have been linked to ice age cycles, are the product of this secular dynamics. They are predictable, bounded, and slow. They are the climatological heartbeat of a flat, well-organized solar system. If the solar system were less flat, if the planetary orbital planes were scattered in multiple directions, and if the secular dynamics were more chaotic, the Milankovitch cycles might be less regular, or their amplitudes might be larger, or the Earth's axial tilt might wander over a much wider range. Any of these changes could have made the Earth's climate history more extreme, potentially disrupting the long evolutionary processes that produced complex life. Some researchers, following work by astronomers including Jacques Lascar, have suggested that without the Moon's stabilizing influence on Earth's axial tilt, the tilt would undergo chaotic variations between 0 and as much as 85 degrees over millions of years. But others point out that the Moon itself formed as a result of a chaotic impact, the Theia collision, and that the presence of the Moon is itself a product of the solar system's specific dynamical history, not a guaranteed feature of Earth-like planets around Sun-like stars. The connections between orbital architecture, axial stability, and habitability are genuine but complex, and the field of habitability studies is still working out the relative importance of each factor. What can be said with confidence is this: the flatness of the solar system is not merely an aesthetic or geometric property. It is functionally connected to the stability of individual planetary orbits, to the regularity of long-term climate cycles, and ultimately to the conditions that allowed complex life to develop on Earth. The flatness is not the cause of life, but it is part of the causal web that made the Earth habitable over billions of years. And that web, in turn, traces back to the conservation of angular momentum in a cold cloud of gas that collapsed 4.5 billion years ago. Something here deserves a moment of stillness. We are, right now, inside this story. You are on a planet whose orbital geometry, its inclination, its eccentricity, its relationship to the other planets' orbits, was shaped by physics that operated before the Earth existed, in an environment that no longer exists, under conditions that we can reconstruct only approximately and understand only partially. The flatness that you can observe in the night sky, that thin band of planetary paths tracing the same arc across the heavens, is the record of all of this. The cloud, the collapse, the disk, the giants, the chaos, the stability. All of it is written there in the constrained paths of those points of light. Now we arrive at the intellectual heart of this story, the place where the accumulation of everything we have learned forces us to face a set of questions that physics, by itself, cannot answer. We understand, in broad terms, why the planets orbit in the same plane. We have traced the mechanism, step by step, from the molecular cloud to the invariable plane. We have identified the key physical law, conservation of angular momentum, and shown how it operates at the scale of solar systems, how it was working billions of years ago and is still working now, and how the same law operates in planetary systems throughout the galaxy. But here is what that understanding does not give us. It does not tell us why the universe has a law called conservation of angular momentum. It does not tell us why space exists in 3 dimensions rather than 4 or 2, a fact that is essential for orbital mechanics to work as it does and for stable orbits to exist at all. It does not tell us why matter, attracted by gravity, forms stars at all. Why the universe didn't simply expand into a cold, diffuse, featureless gas without ever collapsing into structure. It does not tell us what the pre-solar molecular cloud was doing before it started collapsing, where the angular momentum in that cloud came from at the deepest level, and what physical process first set the galaxy's molecular gas spinning. What is angular momentum really? We have a precise mathematical definition: the product of mass, velocity, and radius in circular motion, or more generally, the cross product of the position vector and the momentum vector of a moving mass. We have a law that says it is conserved in the absence of external torques. We have 4 centuries of experimental and observational confirmation of that law, from Kepler's observation that planets sweep equal areas in equal times, which is a direct statement of angular momentum conservation, to the precise measurements of planetary orbits today. The law works. It works everywhere we have ever tested it, at every scale from subatomic particles to galaxy clusters. It is one of the most robustly confirmed regularities in all of science. But why does it hold? The answer, from the deepest level of physics we currently understand, is that angular momentum conservation is a consequence of rotational symmetry, the invariance of the laws of physics under rotation in space. This was established by the German mathematician Emmy Noether in 1915 in one of the most profound theorems in all of mathematical physics. Noether proved that every continuous symmetry of the laws of physics corresponds to a conserved quantity. The translational symmetry of space, the fact that the laws of physics are the same everywhere, gives rise to conservation of linear momentum. The time symmetry of physics, the fact that the laws work the same way today as they did yesterday, gives rise to conservation of energy. And the rotational symmetry of space, the fact that there is no preferred direction in the universe, that physics works the same way regardless of which way you are facing, gives rise to conservation of angular momentum. The solar system is flat because space has no preferred direction. Stay with that for a moment. The reason all the planets orbit in the same plane, the reason for the elegant, thin disk of the solar system that humans have observed and wondered about since antiquity, is that the universe does not distinguish between up and down, left and right, north and south. Space is isotropic. It has no preferred orientation. And because it has no preferred orientation, the rotational motion in any physical system is conserved. And because rotational motion is conserved, collapsing gas clouds form disks. And because collapsing gas clouds form disks, planets form in planes. The flatness of the solar system is written into the symmetry structure of space itself. This is not a metaphor. This is the actual mathematical foundation of the physics we have been discussing. Conservation of angular momentum is not an arbitrary empirical fact, true because we observe it to be true. It is a theorem derived from the geometry of space. The isotropy of space implies angular momentum conservation. Angular momentum conservation implies disk formation. Disk formation implies planetary coplanarity. The chain is logical step by step from the deepest property of space to the observable geometry of the solar system. How far back does the causal chain extend? All the way to the beginning, to whatever conditions produced a universe with rotationally symmetric laws of physics. We do not know, and we cannot know, why the universe has this symmetry rather than some other symmetry or no symmetry at all. We cannot reach behind the mathematics of Noether's theorem to ask what causes rotational symmetry in the first place. That question lies beyond the boundary of what current physics can address, and it may lie beyond what any physics can address. It is one of the places where the chain of causation runs into a wall, not the wall of insufficient data or insufficient mathematical tools, but the wall of the question having no answer within the framework of the laws of physics themselves. Can we know why space has rotational symmetry? No, we cannot. This is not, we do not yet know, but the question of why the fundamental symmetries of physics are what they are may not be answerable within physics. This is the epistemological limit at the center of the flatness story. The chain of causation runs all the way back to Noether's theorem, and there it stops. Not because the chain breaks, but because asking what lies behind the chain's deepest link is asking a question that is not a physics question. What does that mean for the flatness of the solar system? It means that the orderly thing you observe in the night sky, those planets constrained to their thin band across the heavens, is a direct manifestation of the most fundamental geometric property of the universe we inhabit. It is not a coincidence, not an accident, not a special feature of this particular system. It is what the universe does when you give it rotating gas and time. It is written into the structure of reality at the deepest level we understand. And this, in turn, means something about what it is like to look up at a clear night sky and watch Jupiter move slowly through the constellations, constrained to its band, tracing the memory of the disk. You are not just watching a planet. You are watching a direct expression of Noether's theorem. You are seeing, with your naked eyes, a consequence of the rotational symmetry of space. The flat band of the planet's paths is a signature of the universe's deepest geometry, written in light across the heavens. Is there anything that could undo this? Is there any circumstance under which the solar system could stop being flat? Could the flatness be lost? In principle, yes. A sufficiently close encounter with a massive object, a passing star, a rogue black hole wandering through the galactic disk, could gravitationally disrupt the solar system's architecture. The probability of such an encounter on timescales of billions of years is small, but not zero. Over the full remaining lifetime of the Sun, roughly 5 billion years, the probability of a disruptive stellar encounter is estimated to be extremely small, perhaps of order 1 in a million or less, depending on the density of stars in the solar neighborhood over that period. There is also the evolution of the Sun itself to consider. As the Sun ages and eventually expands into a red giant, its mass loss will cause the planetary orbits to gradually expand outward as the Sun's gravitational grip weakens. The expansion will be adiabatic, slow enough that the planet's orbital shapes are preserved even as the orbits grow. The orbits will expand, but the inclinations should remain roughly constant. The flat will be preserved even as the scale changes. Eventually, the Sun will shed its outer layers as a planetary nebula and leave behind a white dwarf, a dense, Earth-sized remnant of the original Sun with roughly half its original mass. At that point, the planet's orbits will have expanded significantly, and the dynamical stability of the system will change. Whether any of the solar system's planets will survive the Sun's red giant phase is uncertain. The inner planets, particularly Mercury and Venus, and possibly Earth, may be engulfed or destroyed. But Jupiter and Saturn, the giants, the guardians of the invariable plane, will almost certainly survive, and whatever remains of the solar system around the future white dwarf will carry within it the fossil geometry of the original disk. White dwarfs, it turns out, sometimes show evidence of rocky material in their atmospheres, material that should have gravitationally settled out of the white dwarf's atmosphere long ago, given the extreme surface gravity of these objects, and yet is observed to be present. This rocky material is thought to be the debris of asteroids, comets, and possibly planets that have been tidally disrupted as they fall into the white dwarf. The composition of this material, measured spectroscopically, provides a direct record of the mineralogy of the original planetary system. Some of these white dwarfs show abundance patterns consistent with rocky, differentiated bodies, worlds with iron cores and silicate mantles, like the terrestrial planets of our solar system. They are reading the fossil record of planetary systems that no longer exist, dissolved into the white dwarf's atmosphere but preserved in spectroscopic memory. In billions of years, a white dwarf somewhere in the Milky Way may acquire the debris of the Earth in its atmosphere. Astronomers in some future civilization, if they observe that white dwarf, will see in its spectrum the chemical signature of what was once a rocky planet in a flat disk. They will see the fossil of a flat. 5 billion years from now, some trace of the original disk's geometry may still be readable in the orbits of Jupiter and Saturn, expanded but coplanar, around a cooling white dwarf. The disk is long gone. The sun is long gone. The Earth may be long gone. But the angular momentum vector of the pre-solar cloud may still be traceable, in principle, in the orbital planes of the surviving giants. The flatness is that persistent. Stand on a hilltop on a moonless night, far from city lights, and let your eyes adjust to the dark. It takes about 20 minutes for the rods in your retinas to reach full sensitivity, for the neural circuitry of your visual cortex to quiet the noise and start detecting the faint. When it happens, the sky does not simply become brighter, it transforms. The Milky Way emerges not as a vague smudge, but as a textured river of light, banded and structured, with dark lanes of obscuring dust cutting through its brightness. The stars resolve from a general glow into individual points, then into depths, layers upon layers of distance receding in all directions. And somewhere in that sky, if you know where to look, you will find the planets. They are the ones that do not twinkle. They are bright and steady, their light coming to you not from a point source, but from a disk too small for the eye to resolve, a disk that averages out the atmospheric shimmer that makes stars flicker. They sit in a line, they follow a band. And now you know what that band is. It is the invariable plane. It is the fossilized geometry of a disk that burned out 4.5 billion years ago. It is the legacy of a cold molecular cloud's barely perceptible rotation, amplified by the most patient and inflexible of physical laws, preserved through the formation of giants, locked in place by the overwhelming angular momentum of Jupiter and Saturn, and maintained across 4.5 billion years of gravitational evolution with no more disruption than a few degrees of orbital inclination scatter. What you are seeing, in the paths of those steady points of light, is Noether's theorem written in orbits. Stay with that for a while. There is no need to rush to the next thought. The understanding we have built together in the preceding hours, the molecular cloud, the collapse, the disk, the angular momentum cascade, the giants, the invariable plane, is not the kind of understanding that needs to be processed quickly. It is the kind that deserves to settle, slowly, into the way you see the sky. This is the moment in the story when the question changes. We have spent a long time asking, how? How did the disk form? How did the planets grow? How did the flatness persist? The how has been answered in broad terms as thoroughly as current science allows. But the moment you stand on that hilltop and actually look at the planets, the how fades into the background and something else rises in its place. Not what or how, but what does it mean? What does it mean that a cold cloud of gas, collapsing under its own gravity, with no intention and no purpose, with nothing but the blind operation of conserved physical quantities, produces a structure so geometrically precise that human beings can trace it with their eyes across the sky? What does it mean that the most fundamental symmetry of space, the rotational invariance that Noether showed underlies angular momentum conservation, expresses itself not in abstract mathematics, but in something you can see, something you can point to, something that ancient astronomers noticed and wondered about long before they had any idea what it meant? And here is the deeper version of the same question. What does it mean that we are among the beings who figured this out? This is not a trivial point. The chain of understanding we have traced is not short or simple. It runs from Kepler's observation of equal areas in equal times, through Newton's formulation of gravity and the laws of motion, through Laplace's nebula hypothesis and its angular momentum problem, through the dismissal and revival of the nebula model, through Safronov's 1969 monograph on protoplanetary cloud evolution, through the development of the solar nebula disk model, through the discovery of hot Jupiters and misaligned exoplanetary systems, through Noether's 1915 theorem and its implications for conserved quantities, through Lasker's numerical simulations of solar system chaos, through Alma's images of protoplanetary disks in Taurus and Ophiuchus and the Orion Nebula, through all of it, a chain of inquiry spanning 4 centuries, carried forward by thousands of people who spent their lives thinking carefully about rotating gas and orbiting worlds. That chain of understanding is itself something remarkable. The fact that conscious beings on a small rocky planet in a flat disk, orbiting an unremarkable star in a spiral arm of the Milky Way, have managed to trace the origin of their planet's orbital geometry all the way back to the symmetry structure of space. This is not a given. It is not guaranteed by the laws of physics that intelligent beings will arise within any planetary system. It is not guaranteed that if they arise, they will develop the mathematics to understand Noether's theorem or the instruments to observe protoplanetary disks at millimeter wavelengths from a high desert plateau in Chile. The understanding did not have to happen. It happened because of a long, branching, contingent history of human thought and human effort and human curiosity. And that history, the history of how we came to understand why the planets orbit in the same plane, is itself embedded in the same flat disk we have been discussing. The civilization that produced Kepler, Newton, Laplace, Noether, Safronov, Lasker, Mayer, and Queloz, all of them lived on a planet in a flat disk around a star. The disk's flatness provided the orbital stability that allowed the Earth's climate to remain hospitable over the billions of years needed for complex life and then intelligent life to evolve. The understanding of the disk's flatness was only possible because the disk's flatness made the understanding possible. The knower and the known are the same thing, seen from different ends of time. This is the kind of thought that tends to arrive at 2 in the morning, on a hilltop looking at the planets. It does not resolve into a clean conclusion. It sits in the chest, quietly, between awe and something that is not quite sadness, but contains sadness the way a clear night sky contains the darkness between the stars. In the year 1543, the Polish astronomer Nicolaus Copernicus published De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, a work that displaced the Earth from the center of the universe and placed the sun there instead. The planets, in Copernicus's model, orbit the Sun, not the Earth. And one of the observations that motivated Copernicus, one of the things that made the heliocentric model simpler and more elegant than the Earth-centered model, was the fact that the planets are always found near the same great circle in the sky. They do not wander freely in all directions. They are constrained to a band. Copernicus could see the flatness. He did not know what caused it. He had no concept of angular momentum, no knowledge of molecular clouds, no notion of protoplanetary disks. He had only the observation: the planets move in a plane. And that observation was compelling enough, suggestive enough of an underlying order, that it helped him see through the complexity of the geocentric model to the simpler reality beneath. The flatness was visible before it was understood. The order was apparent before the cause was known. This is one of the most profound aspects of scientific inquiry. Nature leaves signatures of its deep regularities in places where even pre-theoretical observation can notice them. The planet's confinement to a plane was observable with the naked eye by anyone willing to watch the sky carefully over a period of years. The explanation for that confinement required 4 centuries of mathematical and observational development. But the signature was always there, in plain sight, waiting. How many other signatures of deep physical laws are sitting in plain sight right now, visible to any careful observer, waiting for the 4 centuries of work that will eventually explain them? This is not a rhetorical question. It is a genuine one, and the history of science suggests that the answer is many. The universe is generous with its clues. It is not so generous with its explanations. Immanuel Kant, in 1755, wrote what may be the first serious scientific proposal that the solar system formed from a rotating nebula. Kant was a philosopher, not an observational astronomer, and his proposal was largely speculative. But he saw, with philosophical intuition sharpened by the Newtonian physics he had studied, that a rotating cloud of matter would naturally flatten into a disk as it collapsed. He could not demonstrate this mathematically. He did not have the concept of angular momentum conservation in its modern form. But he saw the shape of the argument, and he wrote it down. Kant was working in Königsberg, now Kaliningrad, a Russian exclave on the Baltic Sea, in the middle of the 18th century, more than 200 years before the first protoplanetary disk was directly imaged. He was reasoning from general physical principles to a specific cosmogonic prediction, and he was right. Not in every detail. His model had significant problems, as Laplace's subsequent version did, and neither version fully solved the angular momentum problem. But the central insight, rotating cloud collapses to flat disk, planets form in disk, flatness is inherited from disk, was correct. A philosopher in 18th century Prussia, reasoning from first principles with no telescope and no data beyond the naked eye observation of planetary positions, identified the correct physical mechanism for the solar system's flatness. There is something both encouraging and humbling about this. Encouraging, because it suggests that the universe's deep regularities are accessible to careful reasoning, even without sophisticated instruments. Humbling, because it took another 2.5 centuries to fill in the details, and because Kant's correct intuition was largely ignored or dismissed for most of the 19th century, when the angular momentum problem seemed to refute it entirely. The history of this particular idea, rejected, abandoned, then revived and vindicated, is a reminder that correct insights sometimes need to wait for the rest of science to catch up. Viktor Safronov was a Soviet astronomer working at the Schmidt Institute of Physics of the Earth in Moscow. His 1969 monograph, Evolution of the Protoplanetary Cloud, and Formation of the Earth and the Planets is not a famous book outside the circles of planetary science. It does not appear on lists of great scientific works. It is a technical monograph, dense with mathematics, addressing specific problems in the growth of planets from solid particles in a protoplanetary disk. And yet, its influence on planetary science is profound. The birth of the modern, widely accepted hypothesis of planetary formation, the solar nebula disk model, can be traced to the works of Soviet astronomer Viktor Safronov. His book, translated into English in 1972, had a long-lasting effect on how scientists thought about the formation of planets. Safronov's work provided the mathematical scaffolding for understanding how planets grow from centimeter-sized particles to kilometer-sized planetesimals to full-sized worlds within the flat disk of the solar nebula. His framework is the foundation on which everything we understand about planet formation is built. And it is a framework in which the flat disk is not an assumption, but a consequence of the same physics Kant intuited in 1755. There is a lineage here, running from Kant in Königsberg, through Laplace in Paris, through Safronov in Moscow, through the collaborations that used the Kepler Space Telescope and ALMA to image and characterize protoplanetary disks across the galaxy. Different countries, different centuries, different methodologies, all converging on the same answer. The planets orbit in the same plane because a rotating cloud of gas conserves its angular momentum when it collapses. The answer has been the same for 2.5 centuries. We have just gotten progressively better at demonstrating it, quantifying it, and understanding its implications. The lineage of this understanding is itself a remarkable thing. Human beings, living brief lives on a small planet, passing knowledge from generation to generation through language and mathematics, and the careful training of students, have managed to maintain and extend a chain of understanding that spans centuries and continents. The knowledge in your mind right now about angular momentum and protoplanetary disks and the invariable plane is the accumulated output of that multi-generational effort. You are the current endpoint of a chain that began with people watching planets move through the night sky and wondering why they stayed in a band. The chain is not finished. The questions we identified, the 7-degree tilt of the sun's equator, the formation of planetesimals across the meter-to-kilometer gap, the distribution of orbital architectures across the galactic population of planetary systems, the role of birth cluster dynamics in shaping disk geometry. These are live, open questions being actively pursued right now. The story is still being written. We are inside it. There is an emotion that arises in this kind of moment, at the intersection of deep knowledge and genuine uncertainty, in the space between understanding what we know and confronting what we do not. It is not the simple pleasure of having learned something. It is something more complex, a mixture of satisfaction and vertigo, of clarity and humility, of feeling simultaneously very small and very privileged. Small, because the universe is so large and old and indifferent to the specific history of one species on one planet in one solar system. Privileged, because we get to know any of this, because the universe happened to produce beings capable of asking these questions and making genuine progress toward answering them. The planets have been orbiting in their flat plane for 4.5 billion years. For the vast majority of that time, roughly 4.5 billion years of it, there was no one on Earth to notice. The flatness existed, and the physics that caused it existed, and the mathematical truth of Noether's theorem existed, and none of it was known or understood, or even observed by any conscious being. The planets just went around, and went around, and went around, And then, in a geological eye blink, a species appeared that was curious enough and persistent enough to watch the planets carefully, to notice the band they traced across the sky, to wonder why, and to follow that wonder through 4 centuries of increasingly sophisticated inquiry until they arrived at a theorem proven by a German mathematician in 1915, which revealed that the flatness of the solar system is a consequence of the rotational symmetry of space. That is an astonishing arc. From wondering why the planets stay in a band, to discovering that the universe has no preferred direction, and that this fact, this deep, abstract geometric property of space itself, is why the planets stay in the band. The question that a shepherd in ancient Mesopotamia might have asked looking at the night sky has an answer that requires Noether's theorem to fully articulate. The distance between the question and the answer, measured in mathematical sophistication, is vast. The distance between the question and the answer, measured in the persistence of human curiosity, is a straight line. What do you do with this? What do you do when you understand, genuinely understand, at a depth that cannot be superficial, that the familiar thing you have looked at your whole life, the constrained paths of the planets through the night sky, is a direct expression of the deepest geometry of the universe? Perhaps the answer is, you look at it differently, not because the sky has changed, but because you have. The planets are still there. They are still steady lights tracing their band across the constellations. But now the band is not just a band. It is a message. It is the universe telling you something about itself in the only language it has. The language of physical law expressed in the behavior of matter. The universe conserves angular momentum. It has no preferred direction. It is rotationally symmetric at every scale and in every corner of space that we have ever measured. And because of this single abstract mathematical fact, when gas collapses under gravity in any part of the universe, it forms a disk. And disks form planets, and planets trace the inherited geometry of the disk across the sky of whatever world forms inside the disk. Everywhere in the universe where there are planets, and we now know there are planets in nearly every solar system, and there are hundreds of billions of solar systems in the Milky Way alone, the planets orbit in a plane, not our plane, not the plane defined by Earth's orbit, not any cosmologically special plane, but whatever plane the particular pre-stellar cloud happened to be, defined by its particular angular momentum vector. Each system is flat in its own direction. Billions of different directions, all of them flat. The universe is full of flat. Flat in every direction. Flat because of a single conserved quantity. Flat because space has no preferences. And on one of those flat systems, around an unremarkable yellow star, on the third planet from that star, beings evolved who could figure all of this out. Who could stand on a hilltop and look at the flat band of planets, and eventually, after thousands of years of effort, understand why it is flat. Who could trace the causal chain from the night sky back through the solar system's history, back through the protoplanetary disk, back through the collapsing molecular cloud, back through the rotation of the pre-solar cloud, back through Noether's theorem, back to the rotational symmetry of space. That is where we have arrived. Not at a conclusion, exactly. Science does not arrive at conclusions, it arrives at better questions, but at a vantage point from which the whole story is visible. The cold cloud, still and dark and vast. The slow collapse, the amplifying spin. The disk, thin and warm and alive with dust and gas. The growing worlds, the dispersing gas. The 4 giants, massive and remote, carry the disk's memory in their orbital planes for all of time. the thin band of planets that any careful observer can trace across the night sky. And now you understand what it is. The solar system is flat. That is where we began, and that is where we return. Not because nothing has changed, everything has changed, but because the best endings in science, as in music, are not resolutions to somewhere new. They return to the opening theme, heard with new ears. Look up at the night sky and pick out the planets one more time. Every one of them, Mercury, Venus, Mars, Jupiter, Saturn, traces nearly the same thin line across the heavens. 8 worlds, 4.5 billion years of motion, and almost no vertical scatter. You knew this at the beginning. You nodded at it, perhaps, as a familiar fact. But the nodding and the knowing are different things, and the past 2 hours have been a journey from the first to the second. We began by noting that the textbook answer, the planets all formed from the same spinning disk, so they ended up in the same plane, is not wrong, but it is incomplete. It is a placeholder for a deeper truth, and the deeper truth turns out to be layered, causal, and profound. The disk is not simply a given. The disk had to be created, and its creation was not accidental, but inevitable, the direct consequence of one of the most powerful and universal laws in all of physics. We followed that law, conservation of angular momentum, from its mathematical foundation in Emmy Noether's 1915 theorem on symmetry and conserved quantities, backward through its application in the collapse of the pre-solar molecular cloud, forward through the formation of the protoplanetary disk, and outward through the growth of planets and the eventual dispersal of the disk that shaped them. We found at every step that the flatness of the solar system is not a special feature requiring special explanation. It is the minimum energy configuration of a rotating physical system. It is what physics inevitably produces when you give it rotating gas and time. We revisited Pierre-Simon Laplace, working in Paris in 1796, who saw the broad shape of the answer before the mathematical tools to fully articulate it existed. We recalled Immanuel Kant, reasoning in Königsberg in 1755 with nothing but first principles and the naked eye observation of planetary motions, identifying the core mechanism 2.5 centuries before ALMA could image a protoplanetary disk directly. We traced the crisis of the angular momentum problem that sent the nebula hypothesis into eclipse for most of the 19th and early 20th centuries, and the quiet, patient work of Viktor Safronov in Moscow in 1969 that laid the foundations for the modern solar nebula disk model. We learned that the flatness of the solar system is dominated, overwhelmingly to the tune of 98%, by 4 giant worlds. Jupiter alone carries 60.3% of the solar system's total angular momentum. Saturn carries 24.5%. The Earth, our vantage point for all of astronomy, contributes less than 1%. The invariable plane, Laplace's invariable plane, the true geometric center of the solar system's angular momentum, lies within 0.5 degree of Jupiter's orbital plane, and it is fixed to a precision of fractions of an arc-second over human timescales. We explored the detailed physics of the protoplanetary disk, its flared vertical structure, its thermal gradient, and the ice line that divided the domain of rocky worlds from the domain of gas giants, its turbulence driven by the magneto-rotational instability, its transport of angular momentum outward from the forming sun through magnetic braking and viscous stresses. We noted that paleomagnetic measurements of ancient meteorites, tiny rocks in laboratory drawers, carry within them a fossil record of the magnetic field environment of the early solar disk, confirming the theoretical picture with direct physical evidence 4.5 billion years old. We examined the growth of planets within the disk, from microscopic dust grains settling toward the midplane, through the streaming instability that concentrates dust into the dense clumps from which planetesimals form, through the runaway accretion that assembles planetary embryos, to the chaotic final stages of terrestrial planet formation, in which worlds the size of Mars collided repeatedly to produce the 4 rocky planets of the inner solar system. At each stage, the flat geometry of the disk was inherited and passed down, from dust sublayer to planetesimal to embryo to planet, so that by the time the disk dispersed, the planets were already committed to the plane. We confronted the genuine uncertainties in this story. The formation of planetesimals from pebble-sized particles, crossing the meter-to-kilometer gap in the face of the inward drifting headwind, remains the biggest unsolved problem in the nebula disk model. The mechanism of angular momentum transport in protoplanetary disks, whether primarily through the magnetorotational instability, magnetic braking, disk winds, or some combination, is not definitively settled. The origin of the 7-degree tilt between the Sun's equatorial plane and the invariable plane of its own planetary system is uncertain, with candidate explanations including stellar birth cluster dynamics, the hypothetical Planet 9, and primordial misalignment in the pre-solar cloud. These are honest uncertainties, and we named them as such. We looked outward to the broader galaxy through the lens of the Kepler mission's thousands of exoplanetary systems and found that coplanarity is common, particularly for systems of small planets, consistent with the universal operation of the same disk physics that shaped our solar system. We found also that coplanarity is not universal. Hot Jupiters are frequently misaligned with their host stars' equatorial planes, sometimes dramatically so, with some planets orbiting in retrograde configurations that appear to violate everything the disk model predicts. We traced the mechanisms: the Kozai leadoff gravitational perturbation, planet-planet scattering, stellar obliquity from birth cluster dynamics that can scramble the orderly geometry of a disk-formed planetary system after the disk is gone. We saw, in the contrast between our orderly system and the most disrupted exoplanetary systems, what the solar system's flatness required. Not just the right physics, but also a history calm enough to let the disk's legacy persist. We traced the long-term gravitational dynamics that preserve the flatness over billions of years, the secular oscillations of orbital planes around the fixed invariable plane, the conservation of total angular momentum that bounds those oscillations, the Lascar chaos that makes the solar system's precise future orbital configuration unpredictable beyond 100 million years, while leaving the system's gross architecture stable on much longer timescales. We noted the 1% probability that Mercury's orbit will be catastrophically destabilized within the remaining lifetime of the Sun. A reminder that stability and permanence are not the same thing, and that the flatness we observe is a long-lived configuration rather than an eternal one. And then we arrived at the deepest layer of the answer. The flatness of the solar system is a consequence of conservation of angular momentum. Conservation of angular momentum is a consequence of rotational symmetry in the laws of physics. Rotational symmetry, the fact that space has no preferred direction, is one of the fundamental geometric properties of the universe. Noether's theorem, proven in 1915, shows that this symmetry implies the conservation law with mathematical necessity. The flatness of the solar system is therefore not an arbitrary fact about the solar system. It is an expression of the universe's most fundamental geometric properties, visible with the naked eye from the surface of one of the worlds it produced. The planets orbit in the same plane because the universe has no preferred direction. That is the sentence we have been building toward for 2 hours. And now that you have it, you can hear it not as a compressed summary, but as a dense, loaded statement, carrying within it everything we have traced together. The cloud, the collapse, the disk, the giants, the invariable plane, Noether's theorem, the rotational symmetry of space. The solar system is flat because the universe is isotropic. The universe is isotropic because, and here the chain runs into the wall we identified, the wall beyond which current physics has no answer. It simply is. The deepest level of the causal chain is the universe's nature, and the universe's nature is not something science can currently explain. It is the starting point, the given, the axiom on which everything else depends. There is a particular kind of intellectual peace that comes from following a question all the way to its honest boundary, not to a false resolution, not to a satisfying story that papers over the genuine uncertainty, but to the actual edge, to the place where the answerable ends and the unanswerable begins. The flatness of the solar system has taken us to that edge. We know why it is flat in every sense that current science can address. We know the mechanism, the history, the physics, the symmetry principle. And we know that the symmetry principle itself has no explanation within the framework of physics. That the question of why the universe has the symmetries it has is not a physics question in any current sense. That is not failure. That is success. The goal of scientific inquiry is not to explain everything. It is to extend the boundary of the explainable as far as possible, and to be honest about where that boundary lies. We have extended it here, from the observation that the planets trace a band across the sky, all the way back to the rotational symmetry of space. The band between the explainable and the unanswerable has been pushed back 4.5 billion years in physical time and 4 centuries in intellectual history. What is left at the end is not a mystery, but a recognition. The flat solar system is what the universe looks like when it is given time and gas and the law of angular momentum conservation. It is the universe expressing its own geometry through the medium of orbiting worlds. The planets trace their thin band across the sky not because anyone arranged them there, not because any external purpose required it, but because the universe is the way it is, and being the way it is, it produces flat disks and flat planetary systems wherever the conditions are right, which is to say, nearly everywhere. You are in one of those worlds. You are made of the same molecular cloud material that formed the disk that formed the planets. The iron in your blood was forged in a supernova that preceded the solar system's formation and injected its heavy elements into the pre-solar cloud. The calcium in your bones was processed through the same stellar generations that built up the heavy element abundance of the galaxy over its first 8 billion years before the sun formed. You are, in the most literal chemical sense, a product of the same disk whose geometry we have been tracing. The flat band of planets crossing the night sky is not out there, separate from you. It is the large-scale expression of the same physical processes that assembled the atoms of which you consist. The angular momentum that flattened the pre-solar cloud into the disk is the same conserved quantity, the same expression of spatial rotational symmetry that governs every spinning particle in your body, every orbital electron, every rotating molecule. The law is not something the universe applies to some things and not others. It applies everywhere, always, at every scale. The flat solar system and the spinning particles in your cells are both consequences of the same truth about space. If this changed how you think about the solar system, about the night sky, about the thin band of planets you can trace from horizon to horizon on a clear night, then the time was well spent. The planets are still there. They will be there tomorrow and next week and 1,000 years from now, orbiting in their flat plane, carrying the memory of the disk. The understanding does not change the sky, but it changes the sky for you. Thank you for staying. Thank you for following this chain from the familiar observation to its deepest root, for sitting with the uncertainties as well as the answers, for allowing the story to take the time it needed. The planets will still be there when you go back to sleep. They will still be tracing their thin line across the heavens, and now that line means something different to you than it did 3 hours ago. That is what science is for.